So welcome to the Friday, so the last day of the 2012 summer school on molecular and multiscale simulation. So what I'm going to start off with is I'm going to give a little bit of a overview of what we've covered so far, reasonably quickly, and then I'll go ahead and move into the topics today, which is to really focus on multiscale simulation. So the first day was clearly to cover molecular. And so clearly in terms of quantum Monte Carlo simulation. Mostly what was covered was Q-walk and some related ideas. But a lot of those principles that were discussed on that first day are applicable to other kinds of Monte Carlo type algorithms. And I'll actually be talking about some Monte Carlo algorithms as part of the presentation and discussions today. And so it was a very good example or exemplar of those sorts of algorithms. In that case, focused very much on electrons and atomic structure. Tuesday and Wednesday was the covering of molecular dynamics. The first molecular dynamics was focused mostly on molecular scale, and then the second day was focused more on coarse-grained modeling of biological systems, but coarse-grained molecular dynamics. Nanamdi is pretty heavily used for biological systems, but certainly, it's an engine you could use for non-biological problems as well. Thursday is when we're doing even more of a transition from molecular scale or electronic to atomic to molecular towards multiscale, which is again this transition through coarse graining. And the talk we had and discussions yesterday was focused on that sort of transition. And then what today is hardcore multiscale. So it'll be focused very much on multiscale. So the hope is there's enough background now to really appreciate or understand easily and be able to discuss this kind of topic. And so what we'll do now is I'll just go ahead and start right away. Now, people can interrupt any time. Sometimes I don't always look up, so you can say, hey, over here. So I can see you. So what I'm going to do is I'm going to cover an overview, I'd say more of an introduction perhaps to multiscale simulation algorithms, and guidelines and pitfalls to avoid. So the field of multiscale simulation right now is not really a field. So what it is it's a large number of semi-independent people trying to develop algorithms, and mostly trying to solve applications. So most of it's just focused very much on application solving. If you pick up a paper, and very often there's very little citation or crosstalk between the different application groups and even among different algorithm groups. So what happens is you repeatedly see certain pitfalls people fall into, or traps they fall into over and over and over again. And I would say that well over half of the papers in this field have at least one of these traps in them. And the traps don't necessarily prevent you from getting a solution, but they can lead to a lot of inefficiencies or lack of accuracy, so poor accuracy. And the thing is about many of these pitfalls is they're actually kind of subtle. So you can do everything where everything seems right and put it together and you've got a pretty bad algorithm. So it's an area where you really want to get things right. So one of the main discussion topics of this talk will be to go through those pitfalls and explain why, give you some examples why they're pitfalls, because sometimes it's a bit subtle, and then follow these guidelines so that you don't fall into these sorts of traps. But before I go there, I'm going to first start with just some motivation for the topic. So if you look at sort of a lot of standard, especially high-tech devices, they involve a lot of different scales, whether they're biomedical systems or whether they are in science systems, or whether they're engineering and technology or microelectronic systems. Here's a picture of a diagram from Intel, which is showing part of the standard sort of a 30-centimeter kind of wafer for transistors. And if you zoom in, this is just a zoomed-in image where it's just showing just the copper part. So this is the copper highway that shuttles electrons around. And if you zoom in on these, so these are like shown here are little tiny wires you can see here, and these are sort of, they're actually wires, though they don't look like it, but they're basically wires with rectangular cross-section used to shuttle electrons around. Let me go ahead and switch this just because when something looks like a lightsaber, a geek has to use it. And so we can see this. If you zoom in right here, these are little electron wires, tiny copper wires that are shuttling electrons around. If you zoom in on one of these wires, this is what the cross-section will look like in using some sort of electron microscopy. And the wires don't have circular cross-section. They actually have like little slit cross-sections, and there's certain reasons for doing it that way. And the length scales we're talking around here are on the order of, 20 nanometers or so, so 20, 30, 40, sort of that kind of range, depending on the type of device that you have. If you're putting something in a toaster, it's probably going to be a lot bigger, for example, than if it's a high-end processor. But in these length scales here are on the order of 30 centimeters. And what happens is that, as mentioned earlier, actually yesterday by Umberto Ravioli, is that you really have to control what's going down to the molecular scale. And if you start to have mistakes, too many mistakes, you destroy the product quality. And so you get a non-working device. So you want to make this device, get all these length scales to work together as you're manufacturing the device, but you want to do it in a way that there's almost no mistakes, so very minimal mistakes. And this is showing up again and again and again. And as technologies continue to develop, it's continuing to become more and more important. Now, when you're looking at these things, though, much of the nanoscale kind of things are sort of very, very interesting. And I do a lot of work in that area, and very, very scientific. But if you really want to go ahead and make money, typically you need kilograms. So you don't need little tiny carbon nanotubes with a picture. You need to do something that's actually producing a lot of product. And so that really forces you to have tiny scales, tiny length scales, and big length scales. Okay, so it's very hard to sort of get around that. And so this is driving this research into systems and understanding systems using multiscale simulation. You need the little tiny length scales to control quality, so you can't have like little holes here, for example, where the wire's not working properly, or gaps in the wire. And at the same time, you need to be able to control uniformity at very large length scales. And the complication is how to best couple widely different time and length scales. Now, for many systems, you don't have to do this. So if you take a separations process, for example, I guess I can't come up with it's hard to come up with an example that's going to reach everyone in the audience, given the different disciplines. But if you look at particular systems, especially like as undergraduate and graduate courses, most of them will be focused on you find the rate limiting step, or you try to find the part that's key, and then you sort of oversimplify the model for everything else. And very often that works. Most of the time that works. And so what you do is you can focus on the key length scales and time scales, and then sort of approximate the other ones. But a lot of this focus on multiscale are cases in which you really need all of these. They're sort of talking between them all, and they're all important. And that's when you're sort of pushed into doing multiscale. And so actually one thing in the group is we try to avoid multiscale in the sense that when we look at a problem, we try to avoid it because it's going to be more work. It's going to be harder. And then we find out, oh no, we're unsuccessful, we've got to do multiscale. We do multiscale, which means we have to develop multiple codes and integrate them and so forth. So it's actually, if you can avoid it, it's actually nicer. It makes the problem easier. But for a lot of these high-end problems, high-tech problems, you can't avoid it. I've already went through this to some degree. I'm going to talk a bit, as one of my examples, of the electrodeposition, which is used to form nanowires in microelectronics devices. And I mentioned how you need to have uniformity over 30 centimeters, or from millimeters up to tens of centimeters. Then if you zoom in, you need to have sort of medium range uniformity on the order of microns, millimeters sort of range. And if you zoom in on the processing of these things, this is how you actually make those wires. You have a little trench that's been etched, pre-etched, and then you deposit using electric field, copper ions that become copper atoms, and you fill up the trench. This is a snapshot at 3 different times. And then eventually you've got a wire. So you're looking at the cross wires. The wire's going into the wall. And so those kind of length scales are on the order of sort of nanometers to micron kind of length scales. And then if you look on the surface, like if you take a zoom in right on the surface of the copper, down here you're looking down at angstrom sort of nanometer scales. And all these are important. So if you don't control this very well, if this gets too bumpy, then when you try to deposit this, when you close this gap, you'll have gaps in there. And those gaps is a big problem. So your device will fail if you have electrolytes, a liquid electrolyte in your device that's trapped. What will happen is once you start to turn on the device, copper will start to go into solution and move downstream. And as it keeps moving downstream, eventually you'll remove enough copper, you'll get a short, and then you no longer transfer electrons through that route. So it's pretty important that you get all of these things filled in. But to do that, you need to have very, very good control of this. If this gets too rough, when these things come together, they're too rough and they don't close in. You get liquid there, and then that's a problem. So you need to really control down these length scales, but you also need to control the uniformity along these. If you have too much height on one section, let's say over here compared to here as you're depositing, so along this you're doing a whole bunch of wires across the entire device, 30 centimeters. And so if you have too high on one end, you're going to have to do a lot more chemical mechanical polishing to get down, and you have a lot more chances of potentially causing problems, as well as slowness in operation due to that step. So you don't want to be doing that. So, and then here you of course don't want to have part of this too short and too long and lower and high. You're throwing out a lot of transistors. So now this picture is a picture I sort of put together about, I don't know, 10 years ago maybe, but I keep making improvements so it's more colorful. But what we have here is sort of a snapshot of what are the, if you're trying to solve a problem, where do you need to focus? So if you're looking at very small length scales, so sort of electronic and a little bit bigger than that, atoms and small molecules, you're typically running a quantum chemistry like calculation. You can do larger molecules if you use a sufficiently simplified expression for the way you're trying to attack Schrodinger's equation. If you're using those sorts of approaches, it just shows an example of an orbital. And so here you can look at relatively small length scales. And there's Schrodinger's equation right there. Then you have these sort of other length scales, and now we're looking at things, maybe proteins, things a bit larger. And then we can actually simulate, really up to maybe a nanosecond or so. Key row calculations, certain situations you can do bigger than that. And then you have a lot of work in materials is really in this Kinetic Monte Carlo. Sometimes they call it Gillespie's algorithm or continuum time Monte Carlo algorithms. You get a lot of work in this range because this allows you to simulate up to maybe hundreds of seconds. So maybe the time that you would do something, you actually manufacture material. So you end up having a lot of stuff really in this range. So then we can do much larger time scales. And then length scales, we can get a little bit bigger, especially if you're doing some coarse graining. And there was coarse graining talked about on Thursday. And these are all, so this is all described by F equals ma, basically, with some stochastic terms perhaps, but still basically Newton's law. This here is described by some sort of transition probabilities. And the way you're doing things much longer time scales and length scales is because you don't simulate the path that the atom moves at all times. So you take molecular dynamics, I've got let's say an atom, and now I've got to track the position of that atom as a continuum. So as it moves around in a system. And if I have molecules, then I've got them sort of tethered, I have constraints, and then the whole thing has to move. That ends up being very slow because I have to simulate everything. All of continuum, I have to do all of that. And very often you have systems that was shown, for example, and discussed quite a bit on Tuesday and Wednesday, where not much happens for a while and then something happens. So you end up having to simulate all this stuff when not much happens and then when something happens. And you're simulating all of that as a continuum in space, and so that becomes very computationally expensive. So one way of thinking about the way chemical Monte Carlo works is that what you do is you define a lattice for the positions where the atoms are going to live 99.999999% of the time. So almost always they're going to be in these particular positions. So a good example is a surface where you have lattice sites, where you have maybe threefold holocytes that are energetically favorable. And the atoms will exist there almost all the time. Now, they do move, so they might diffuse along a surface, but the time that they spend in between the one lattice site and another lattice site is very small. And there's nothing interesting about that transition. So what you do is you cut out having to simulate that atom moving from one site to the other site. And you cut out all that very fast dynamics required to simulate that particular transition. And by cutting that out and replacing it with transition probabilities, that you can make self-consistent with molecular dynamics, so it's still self-consistent, but by not actually simulating that, by just having the atom poof, disappear in one place and pop over to another place instantaneously, you're able to do much longer timescales. So that's one way to think about why Kinetic Monte Carlo can really go farther. You're losing some information, but information you don't really care about on the position of atoms between transitions, but then you're able to access many, so like many orders of magnitude in timescales, like hundreds of seconds, for example. So that allows you to pick, get to quite a bit larger. And then Kinetic Monte Carlo is also easier to coarse grain typically than a molecular dynamics code. And I have lots of papers on that. I can point to other people on papers on that about why that is. But the gist of it is that you're moving things around on a surface. representing things as clusters, you can represent, you can basically represent groups of atoms, and then you can self-correct the kinetics so you can ensure that it's self-consistent with atomic scale, as of course, as the groups of atoms move down to one atom, as well as being self-consistent with continuum scale. And so there are papers out that explain how to do that. And so that's the easier thing to do when you've got a nice, well-defined lattice than it is if you're dealing with something like a protein where you don't have a lattice. Now there's another length scale. This particular time and length scales, so our group does a lot of work in this particular area. It's done a lot by people that look at particles, drops, colloids. They really look at this scale. The name of this scale varies. Sometimes when people say mesoscale, they mean this scale. And people I interact with are typically chemical engineers, physicists, stuff. They would usually probably use it this way. But if you're talking to an environmentalist, a mesoscale might be like a mile, you know. So there's a little bit of variation in length scales. But I'd say this is probably the most predominant time and length scales people would look at. It's quite a bit fuzzy, which is why I don't have numbers here. In this case, you're doing some sort of simulation where you're typically representing it something like this. So you have some sort of stochastic type differential equation. You've done some sort of discretization. And so this is a stochastic term, and then you've got some other sorts of discretization terms. These could be PDs and ODs. The kind of descriptions could be what are called population balance equations, or they could be Langevin-like equations, or Fokker-Planck, or so there's a whole variety of sort of continuum-like equations that allow you to simulate tiny droplets and the nucleation of particles and things like that. So there's a whole other group there. I won't spend a lot of time talking about that during today, because there's a whole bunch of issues just in simulating that, much less when you link it to other scales. But we have a lot of papers on this. People are interested. I can give examples where there's a lot of coupling through these kind of scales that have solved some pretty complicated problems involving nucleation of crystals, for example, and tracking the distribution of crystals, but doing it in a large system with turbulent fluid mechanics and turbulent eddies and a whole bunch of other stuff. So there has been quite a bit of advance in here. I say a lot of it's sort of fluids plus kind of people, but there's quite a few, and soft matter physics kind of people. And then you have the continuum scale. So this is typically things that are represented by usually deterministic PDEs. And so there's an example of a conservation equation where you have a species concentration I. Partial with respect to t is called the accumulation term. They have the standard convective term, so you use the velocity. This would be u dot del c, standard term for convection. It's basically a mole balance. You're doing a balance on the number of moles of the species. Then you have a diffusive term, that's a diffusion coefficient, and they have some reaction terms. And there's, of course, a huge amount of literature on this that goes back decades in every engineering discipline. But the point about this is if I want to go ahead and solve at this particular time and length scale, I can't be using this method, at least not by itself. If I want to solve this scale, I can't be using this method. So different types of methods and different types of really models and different types of algorithms are appropriate at different time and length scales. So, and so if you want to solve a particular problem, you'd like to have a method that gives you the best predictions at each of the scales. Okay. And that's what really motivates multiscale, is that if I have a problem where these length scales are important and these length scales are important, if I can use this for the big length scales and these for the small ones, then I can do a coupling. I'm sort of using the best for the best. So the best method for the best length scales. But I can only do this if I can handle the coupling. Okay. And that's where there's a lot of people are trying to do, but it's really quite challenging. So what I'm going to show you here is multiscale simulation is rapidly growing. So this is a little bit of out of date, and I'll show the updated one on the next slide. So if you go to ISI and you search multiscale model and multiscale modeling, and, well, you got to do both because there's the UK spelling and the American English spelling, and multiscale simulation, you end up, can calculate using ISI, you do what's called citation report, and it'll give you the published papers in each year. And you can see the field started somewhere around the mid-1990s, really. And that was about, I was lucky enough, and several people on this campus were lucky enough to start right about then. And then the field went exponential sort of explosion. And then the impact and citations exploded. But it turns out this is actually greatly underestimates the numbers. So I'll show you the real numbers, or a more accurate estimate on the next slide. But before I do that, even if there's a lot of interest and a lot of motivation and problems, you need funding. Okay. But it turns out about 5 years ago, all of these agencies mostly independently, sometimes in collaboration, got together and they wrote down their strategic plans for the next 5 or 10 years. And in all the strategic plans, even EPA, I don't have EPA listed, but saying multi-scale simulation. So it's all this, saying, look, this is what we really need to solve. This is a grand challenge problem. We really need to solve this because we have real problems in engineering and science that need to be solved. And so some of them had joint programs. And then you have, NIH, of course, has its institutes. There's sort of a computational mega grouping within the federal government that includes many of these different branches. Now, what I did just last night is I went ahead and updated. Now, I couldn't go all the way back because there's a limit in ISI for 10,000 papers. And so I wasn't able to go all the way back. But I was able to get the numbers down to 2005 and still have about 10,000 papers. And what I did is I did the same search, but in this case I also put a dash in the multiscale, because a lot of people do it, put a dash there, to get a more accurate estimate for the size of the field. And what you can see here is this is the published papers per year. And we're now approaching almost 2,000 papers per year in a field that barely existed 10 years ago, 15 years ago. Now again, it's not really a field because it's not really coherent. There's a lot of stuff very independent and don't really talk to each other. But at least the overall size of people working in this field has gotten large. The number of citations now is on the order of 20,000 citations a year, which is pretty healthy for a field. And if you still growing quite rapidly. Now, another reason we might want to consider it, this is a NSF report that was out in 2006. What it was NSF put together a blue ribbon panel. They do this occasionally for different kinds of topics. In this case, their question was to identify in simulation-based engineering science, so engineering that's enabled by simulations, what are the challenges? What are the challenges? And it's a report, maybe, I think it's like 100, 150 pages, something like that. So they put on all these experts in computer science, engineering, as well as some in regular sciences. And it turned out that they listed the #1 challenge is multiscale. What was interesting about it was that it's really fun for me to read because like every third page at least there's the word multiscale. So it's pretty pervasive. And then there was a nice science article on theoretical chemistry. Now the article was not on multiscale, so it was on theoretical chemistry. But when you actually read and looked through it, there was a clear understanding about multiscale. And what was interesting is a lot of the comments that were made in the engineering fields, 10 years earlier, but it was sort of picked up by the chemists. So this is like great. This sounds like it was written by a chemical engineer, but even though it's written by sort of a material/chemist/physicist. So major unresolved issues include how to transfer heat and mass across all scales, which is something, of course, engineers care about, as well as some physicists. Coarsen or refine representations seamlessly and adaptively, quantify uncertainties, and there's been quite a bit of work on that in the last 10 years, and extract new concepts and physical laws from such simulations. So that's the motivation. So kind of a long motivation, but it'll sort of, hopefully you can use some of these in your talks. So now what I'll do is we'll go through an introduction. And the way I'm going to do this is I'm basically just going to try to walk through it. I'll try not to go too fast, so you can sort of holler if I do go a bit too fast. And I'll just sort of then sort of just walk through carefully as an introduction through multiscale, but eventually get to some pitfalls that are a little bit more advanced. But I'll try to keep the examples pretty simple so that we can illustrate very clearly what the issues are. So we mentioned about quantum mechanics. Now, these aren't all molecular simulation techniques, so there's some. But I'm going to summarize these because it's multiscale. We're going to be linked to molecular simulation. And even all these statements that are said are not 100% necessarily correct, as you might find some algorithms on these categories that don't completely satisfy this. But the statements are true for the majority of each of these simulation methods. So Monday was covering quantum mechanics. So we had ab initio, semi-empirical, density functional techniques. There's a bunch of methods there. They're very useful for estimating potential fields and estimating kinetic parameters for some systems. So you can get fields. The fields aren't always good for estimating kinetic parameters, so to tell you like the rate of a chemical reaction. But for some gas and solid state systems, they don't do too bad. Then you have molecular dynamics, which was the topic for Tuesday and Wednesday, which solves Newton's equations of motion for atoms to compute time-dependent types of things. You can compute things like diffusivities, for example. So it's a parameter that will influence the dynamics of a system. This applies typically for very short periods. There was a mention by Ahmad that you can actually, there's one guy that's maybe taking it up to, microsecond, but for the most part, or one group, but for the most part, it's really down at the smaller scales. What's very nice about molecular dynamics is trying to gain insights. And then we have a KMC, simulate dynamic processes over lattice for time periods of seconds or more. And it's often the preferred approach if you have transient dynamics of molecular systems. So they're small, so they're stochastic, so you need a stochastic method. But you also need longer time scales. And if you look at these, there is a very natural way of coupling these, at least from the point of a handed-over-the-fence kind of approach. So for example, you use quantum mechanics to give you a potential field. You could feed those potential fields, at least theoretically, into the molecular dynamics. So molecular dynamics uses those to calculate its forces. And then it can calculate parameters, let's say like a diffusivity, and that diffusivity could be used in Kinetic Monte Carlo. But it's even a little bit more sophisticated than that, because molecular dynamics you can use on surfaces to see what are the most likely pathways for molecules to move, or atoms to move, as well as to react to form molecules. And as you do that, you can see what are the most likely events and what are the most likely paths. And once you've done that, that can help you define what are the different pathways you want to allow in your Kinetic Monte Carlo. And so you might have a particular configuration where a molecule's on a surface and might move in a certain way as it moves to another site. So you run a whole bunch of molecular dynamics to figure out what are the probabilities of those different configurations. And then you can take the high probable ones, the ones that cover, let's say, 99.9% of the possible configurations as the reaction occurs on the surface, and feed that as allowable transitions in your chemical Monte Carlo code. So you can actually make this fairly sophisticated from doing molecular dynamic information passing or sort of defining how you formulate your KMC code. And so these are clearly things that can be methods that can be coupled. I'm going to focus actually not so much on that per se. There'll be some discussion of this this afternoon. But I'll be focused more on when you're actually trying to solve things really simultaneously as opposed to really sort of solving something and then feeding it into another code. Now to do this, I'm first going to have to cover Kinetic Monte Carlo simulation. Not because it's a multi-scale method, but just because it hasn't been covered yet in this particular workshop. And we really need, and it is an important method, and it is a method that we're going to need for the examples I'm going to cover. So I'm going to cover a little bit more about this Kinetic Monte Carlo simulation method. Now the chemists and the chemical engineers call it Gillespie's method. And if you don't call it Gillespie's method, sometimes they get very angry. It's kind of weird. And Gillespie, I guess, was a chemist, and so they want to get credit. But if you actually look at it, the people who did this work was done much, much earlier, back in the 40s by mathematicians, and then picked up by material scientists and physicists, much, much earlier than Gillespie. And the advantage of the earlier work is it included diffusion, which is very, pretty important. So it actually allowed the atoms, sort of to move on a surface and to have spatial variations. And so generally, the materials people, physicists, we tend to, refer to that literature because it's richer and earlier. And so we will typically call it Kinetic Monte Carlo simulation. But in the literature, you can sometimes, if it's a chemist or chemical engineer, they'll typically call it this. Sometimes you also hear it called continuous time Monte Carlo, occasionally. And what the KMC method does is it allows you to simulate structural properties of matter that cannot be represented by a continuum description. And so a good example of this would be, let's say, some atomic level surface roughness. So you can't really simulate that using, at least not very well, trying to use a partial differential equation formalism. But even if you used a PDE formulation, if you rerun the simulation, you get different answers every time because of the characteristics of randomness, the stochasticity associated with atomic and molecular motion. So if you did run a PDE, you'd have to feed it stochastic, and then feeding stochastic can make it slower. It's going to be a big headache. So what you'll do instead is instead of trying to represent something that is not well represented by ordinary differential equations or differential algebraic equations or integral partial differential equations, what you'll do is you'll just define the lattices, and then what you'll do is you'll define these each as a configuration or a state. So this here will be one configuration, that'll be another configuration, that's another configuration. And then you define a lattice that'll tell you the positions and identity of atoms on the lattice. So these red ones will be one kind of atom. These will be some other kind of atom. Now, Monte Carlo is actually more general. Kinetic Monte Carlo is more general in this, in that you can also define more complicated things than just really a simple lattice. But for this, I'm going to keep the types of methods relatively simple and focus mostly on problems with simple lattices. So in this case, the lattice would just be each of these sites made in some rectangular or similar kind of grid on a surface. And then I could have a lattice that goes up. So I have a three dimensions. So you have x and y, and then you have a z position that goes up. Now, the way these kind of algorithms are formulated, the actual equations you're trying to solve, in some sense, is very easy, and in some sense, is very difficult. So what we have here is an example of one of those surfaces. Here we have a bunch of copper on a surface. And this would refer to a particular state or configuration. We'll call it sigma. Now, you can write the fundamental equation describing the time evolution of this surface. And that fundamental equation is called the chemical master equation. And you can interpret the chemical master equation in terms of a conservation of probability, where this P is the probability that the system at any time is in this particular configuration, sigma. So this is a single ordinary differential equation describing the probability that the system is in this configuration at time t. And then what you do is you have an in term, so in minus out equals accumulation. So it's a standard conservation equation. And if you want to calculate the rate of production of this particular configuration, you take all the other configurations in the system, then you multiply it by the transition rate that a system in configuration sigma prime will come into sigma. So that will give you the in, and you sum over all the other types of configurations. So this is giving you the rate at which configurations can transition into the configuration sigma. And this one is the rate at which this particular configuration can transfer into other configurations. And each of these possible configurations, you only really have to sum over the nearest neighbor ones, the ones that are accessible to this configuration. And so the ones that are accessible would be, for example, is I might have an atom at one site, let's say here, moves one over. Okay, that will make a new configuration. Okay, and I have to work out what its transition probability is. That would be the W from this configuration to the one in which that one atom moves to a nearest neighbor site. You could have a new atom maybe absorb on a site. Maybe an atom desorbs off a site, so it goes off into solution or into a gas phase. You might have an atom that reacts with another atom and forms another atom. So each of these possible physical, chemical types of interactions, those are all written down carefully. And then you can write out all of this transition probabilities based on the rates. So if you know, for example, the molecular diffusivity on a surface, you can stick that surface diffusivity into a formula that will compute this transition probability. If you know a chemical reaction on a surface, there's a somewhat straightforward formalism that allow you to rigorously derive this transition probability. And so this is a function of all the kinetics, chemical kinetics and diffusivities, for example, in the system. So all the physics and chemistry show up in these transition rates. Now, in some sense, this equation is very simple, right? If you look at this equation, it's linear in the probability. So it's a linear equation. And linear equations are the easiest thing to solve. It's an ODE that's linear. I could, solve that numerically just using Euler's method. Except the problem you run into is the number of configurations. The number of possible configurations, even for a relatively simple system, can be on the order of 10 to the 10, 10 to the 15. So the problem is you end up writing if you try to write an ODE for all of those, you might get 10 to the 15 ODEs. And you don't have enough memory or computation to even dream of solving that. And that's why most people don't try to solve this. Now, there is work by a lot of people that do. I'm one of the people that work in this field. Most people are mathematician types, where we actually try to solve this, either numerically or analytically, but coming up with clever tricks and scaling, sparsity, symmetries, so all kinds of tricks like that. So there is an effort to do that, but those methods will only allow you to handle pretty simple systems. So for example, we can do like crystallization in nanodrops or various types of phenomena with carbon nanotubes. So things that are relatively simple, have certain symmetries, certain properties, you might actually be able to solve this numerically or analytically. But if you end up doing most problems, anything with complicated chemistry, for example, there's no way you're going to solve that numerically or analytically. And so that's why people usually can't go the approach to trying to solve it directly. So what they do instead is they just try to calculate a possible trajectory. Now, in physical chemistry, you would call that a realization. So it's a particular trajectory that the system could follow in time. And so what you do is you'll follow these transition probabilities, and then you allow the system to move, and it's the stochastic system. So you look at the simulation. So that instead of trying to simulate probabilities, you just try to simulate a possible configuration. And so you use these transition probabilities to figure out what is the probabilities that something happens. You pull from a random number generator. It picks a particular event. You operate that event, so you move from one configuration to another. Maybe you move an atom from one site to another. And then you repeat, and you repeat, and you repeat, and you repeat. And there's a bunch of physics and mathematics you can look at that will tell you what the delta T should be and what the stochastic should be, so that that realization is 100% consistent with the chemical master equation. Now, after you're done, you'll have a particular realization. So a particular pathway where the configuration may have started with, let's say, no atoms, and then it adds atoms in one thing. At a time, things diffuse, etc. And then you get some surface. Maybe you get this surface here. Then you rerun the simulation, and then you rerun the simulation. And as you rerun the simulation, you'll get new realizations. And then you can take averaging of some sorts of statistics you might care about. So you might care about, let's say, the surface roughness or the yield of a chemical reaction. So what you'll do is you'll just keep reporting those as a function of time, and then you'll average over time to be able to figure out what is the, roughly, an approximation for the mean behavior of the system. So this field of doing the chemical mass, the kinetic Monte Carlo simulation is actually bigger than chemical mass equations, in that a lot of the literature will write down the equation for KMC that they're implementing their code without even understanding or realizing or writing down this equation. And some of the people are not even aware of this equation. And the reason is you can actually write the KMC formula directly without writing this formally. And so it's actually somewhat easier to write down each of these steps separately and write the KMC out. It's actually simpler than writing the chemical mass equation. So it's not that it's hard, it just requires a little bit more sophistication. So very often in literature you won't even see this listed. You'll just see the transition rates, to see the steps in the algorithm. So what is the issue? Well, typically with manufacturing, very often you're using this equation because it can access these hundreds of seconds kind of timescales that you're going to do for manufacturing. But at the macro scale, you've also got deterministic codes. They're simulating fluid mechanics, for example, Navier-Stokes equation. And now you have to be careful because this is going to have a very stochastic signal, because instead of solving this, you're solving this realization. That realization will be noisy, and you're going to be feeding that noise potentially into a deterministic code. And that can be problematic, because now you're feeding a bunch of noise into something that's a finite volume, finite difference, and finite element code. And these codes aren't really designed to be, getting a bunch of noise. And if you get a bunch of noise in there, a lot of the underlying assumptions you made about continuity of the inputs and stuff will be gone. And so that inherently leads to a rather challenging problem when you use these codes for multiscale simulation. Now, before I go in and really get hardcore really into the overview of multiscale simulations, what I want to do is just talk a little bit about the tricks you use to try to simplify the stochastic simulation before you couple it. So anything you can speed up the stochastic parts of your multiscale simulation first without losing too much resolution, you want to do first, okay? Because that'll immediately transition into the reduction of the cost for your multiscale code. Usually, the stochastic simulation part is more than half of the cost at a given resolution. So if you can reduce this by a factor of, let's say, 10, you'll reduce the overall code by a factor of 5. So typically, you'd like to be able to speed this up. So one technique is coarse graining, which was mentioned in the last couple of days of the workshop. And one common coarse graining is where you track clusters of atoms. So that would be one example of coarse graining that's pretty common. And so that's one way of trying to speed things up. There's some weaknesses of this that were mentioned before. So one weakness is that it's hard to coarse grain without messing up the stochastics. So very often when you coarse grain, you can make what you're computing either noisier or less noisy than the real atomic scale simulation. And there's a lot of literature on this, a lot of discussions on this. I cite a lot of it in this book chapter. And there are a few rigorous ways of coarse graining, but there's only like a couple papers, and it's very difficult to do. That really captures the stochastics correctly. You can still use this for useful things, though. If you're doing something like growth on a surface, that may be fine. That's not such important in terms of stochasticity. But if you're doing the nucleation of trying to calculate nucleation rates for atoms coming together to form crystals, then coarse gradient kills you. Okay, so you'll get all the stochastic draw, all your nucleation rates will be raw, and it'll be really bad. So, and so it really depends very much on what you're trying to solve. And it also means that when you're trying to develop any simulation, but especially multi-scale, you need to really understand what is it you're trying to compute, so you understand what the trade-offs are, and that what any sort of shortcuts you do aren't going to hurt you too much in terms of the answers you're going to get. So, and for multi-scale, it's a bit more because you need to do that for every separate scale or every separate code that you're looking at. Now, another trick that's been pretty heavily exploited in the last 10 years ago is exploiting timescale separation within the stochastic simulation. And so timescale separation, of course, is another type of multi-scale. But if it's only timescale, there's a bunch of tricks that'll deal just with timescales. And so if you can do those tricks to simplify the timescale part first, then when you do the coupling for length scales and stuff, again, that'll be much, much faster. So this is a case in which typical type of techniques they'll do is, let's say, quasi-steady state approximation. So they'll have some dynamic that's so fast, it's really, really fast that they don't really care about, or they know what's going to happen during the dynamic. So what they'll do is they'll do a thing they'll assume like a quasi-steady state, where they essentially assume that certain reactions reach a quasi, like almost steady state phenomena very quickly. And then they'll insert that in the code, and then they don't have to simulate the very fast timescales anymore. Okay, so that's one of these very common tricks that are used in kinetic Monte Carlo simulation to deal with really fast timescales that don't really influence the phenomena that you're trying to simulate. And I cite quite a few of those also in this book chapter. And then, of course, you can use parallel. So there's various types of ways of parallelizing your stochastic simulation. So now I'm actually going to really getting into multi-scale. So I think we have enough background now, kinetic Monte Carlo simulation and molecular simulation. We now really sort of talk about multi-scale. So we're going to go right now back to the roots. So the roots were really back in the mid-1990s. Now, numerous papers existed before that, or several papers existed, where they do things as coupled in a serial-like fashion. So, and I mentioned that a little bit before, where you might take a potential field from a quantum code, feed that into a molecular dynamic code, so that it uses those potentials to compute, let's say, molecular diffusivity, and then feed that molecular diffusivity into KMC code. So that sort of notion started to become sort of more and more of interest, or more and more sort of picking up people, really around the mid-1990s. I picked out these papers. These aren't really the first papers, but they're probably the first papers that made a big impact. Was this Coronel paper, as well as this Maruda's paper, and this Hansen paper. And then there were various people that were sort of follows on that, where you compute something from one code and just use it into another code. They called it multi-scale, and it is multi-scale, but it's not sort of dynamically multi-scale. So in the sense that it's not small scales and big scale codes talking to each other at the same time. Now, this is a very high impact paper that was actually done in 1996. What this did was this did something that was kind of magic. So what they had is they wanted to, let's say you want to understand a problem, let's say crack formation. And you want to be able to simulate right when the crack starts to form and then sort of take off. And so one of the things that they did very early was to really describe what happens at the beginning of a crack, you really need atomic scale. Otherwise, you can't describe it. Not really. You can't really understand what's going on. So what they did is they said, OK, well, what we're going to do is we're going to do our atomic scale there. And then we'll take our, I think it was finite element method. Yeah, finite element mesh. We'll make it macroscopic away from the crack, because you don't need any fine resolution there. And then they resolved the finite mesh all the way down to the atomic scale. Okay, kind of very impressive. Certainly it's impressive in 1996, I can tell you that. And so it's very, very impressive stuff. Now, that's not going to work on most systems. Most systems, you don't have enough computational power. You're going to resolve down to those scales. That one they could do because it was all just a solid mechanics problem, you know. So there was enough simplifications in the problem that you could do it. Not easily, but it could be done. If you try to deal with these much more complicated systems, let's say a protein or something, there's no hope you're going to be able to do this. But it was a very interesting approach that could be done. Now, another approach was to use iterative algorithms, since that was proposed in the late 1990s. Most of these were focused more on coupling continuum codes. So they might have a continuum code for a large fluid domain and then a small fluid domain. And then the idea is they wanted to keep the code separate because they didn't want the timescales to really interact and length scales to interact more than necessary. So they would run these two codes, and then they would iterate between the two codes. So, and especially if you're going to do steady state, then that's something you could do this fine. Now you could argue, why don't you just do the whole thing at once? Well, you might have a case in which you have a code that's really good at one set of length scales, another one that's really good at other length scales. And you don't want to rewrite all the code from scratch because that would take too much time. So what you do is you just run the two codes, and then you just keep iterating boundary conditions until you converge the two codes together. And then that will be a lot easier to implement. Okay, so as long as you can get convergence, you don't have to rewrite any of the two codes. You're just calling somebody else's codes and getting them to iterate together. So in certain cases, that can be a very, very powerful approach in terms of reducing the time it takes for you to write a code for a multi-scale system. You just take codes that are already out there, but make sure you iterate the boundary conditions to convergence for the codes. Now, what became more interesting as you started to get into the late 90s, into the early 2000s, was this notion of simulating dynamical systems, in which you have tight coupling between the time and length scales. And so these are called concurrent multi-scale simulations. So one of the early papers was actually probably the simplest, but was a very high-impact paper, was to use an effective reactivity to link an atomic and continuum scale code. And so what they did in this paper is that they were basically using a physical etching process. And so they're shooting atoms onto a surface. And then the problem is that this thing is doing the atoms. This here is a atomic scale type code, but they wanted to do a continuum code to map what was going on in the inside the trench that they were forming. And so what they did is they wanted to so as it bounced down, they wanted to atom hits. They wanted to do some computations to figure out whether it would form a reaction. It was actually a physical-chemical or chemical-physical etching process, and then they would. They did calculations on a time scale to figure out when an atom hits, what is the effective reactivity? So what is the proportion of times when it hits that it's going to react with the surface? Okay, and then they just fed that effective reactivity to the continuum code that was mapping the interface location. So it was a very simple kind of coding. The effective reactivity was not a boundary condition, right? It was basically a parameter going into a chemical reaction on a lower level code. But it was multi-scale, so it was a way of coupling. It actually was very easy because you do a whole bunch of atom motions, so you got this one number of effective reactivity almost deterministic. Because you could do a whole bunch of atoms and get almost a deterministic number you put into the continuum code. So the continuum code ran great. So, but it's a pretty specialized application. You're not going to be able to apply that kind of approach to most systems. But it was very high impact for its time. Now, another early paper was by Dion Blachos at Delaware, in which what you do is you run each code simultaneously, and then you update the passing of the boundary conditions between the codes. So to understand how this goes, so you've got two codes and they're running in parallel, okay? And then what you do is that I'm going to do a forward step, let's say like an Euler, based on the past states. So I know the states over here, and I know the states over here. And then what I do is I do a step forward, and then after I forward, then I pass the boundary conditions that I had. So at each step, you're passing either the boundary condition from the previous step or well, let me back up. There's a couple different ways of doing this. Okay, so let's do this let's be much more precise. So I have two codes running in parallel. What I do is I might iterate forward in this code and then pass the future boundary condition or its current boundary condition to the other code. Then from this code, I step it forward, and I can either use the boundary condition from the other code or its future if it was computed beforehand, and then I step forward. So there's a couple different variations, but in each case, it's not iterating the boundary conditions. It's only passing the past boundary condition or a boundary condition that just was computed for the other code, and then it's just marching forward. The advantage of that approach is that because there's no iteration, the computational cost, and because it's very easy to parallelize, because you're only matching conditions for a very short time and rarely, especially if each of these codes are pretty computational, it's relatively easy to parallelize. And with no iteration, the cost is basically the cost of the slowest code. So you can choose all your resolutions so that the codes run and finish at about the same time, run it on a parallel computer, and you don't have an extra cost associated with iterating between boundary conditions. So The other advantage of doing this is that if one of your codes is stochastic, you have to be very careful about iterating with boundary conditions. Because if you have a stochastic code, let's say KMC, and you run it, you'll get some sort of updated condition on the interface, let's say a flux or a concentration. But if you try to iterate, you do a tweak to the input, and then you run it again, you get a different answer. So the only way you can prevent that is you have to fix your random seed, okay? That you start the KMC to sort of make it behave like a deterministic code. But then you have problems because then the time scale can shift. So there's a lot of things that make that not iterating very difficult when you really have stochastic code. So to iterate, you've got to converge to something. And if you've got a stochastic code giving you a different answer, a little bit different every time, you're not going to converge. So, and so there's tricks to get around that, and I'll talk a bit about that later. But the point is that doing this case where you run the code simultaneously is much easier because you're always just passing the information forward. So you don't have to try to worry about trying to iterate something that's a stochastic varying type variable. And I'll talk more about this, and I'll have examples later in the presentation. The other approach, which we've already talked a little bit, was this idea of revising the internal iterations to force convergence. So you might have one code that's computing as an output of flux given the concentration, and the other one's computing the concentration given the flux. And then you just keep iterating it too. So you feed the concentration to one, it computes the flux, feeds it to the other one, feeds the concentration, you just keep iterating. So, and so you can do that dynamically, okay? So in steady state, it's of course very rigorous, but in dynamically, you can do the same thing. So you can just update the boundary conditions as you're moving in time. And if you go all the way to convergence, that'll also be rigorous because then you'll force a convergence within each time. Computationally expensive. This particular example was all deterministic, so you didn't have to worry about the stochastic issues of trying to iterate to convergence. And then the other trick you can use is to update the continuum codes much more slowly than the atomic scale codes. And that's the trick that we published a while ago. And that allows you to average a lot of the noise. And so I'll have some examples of that later. And the idea here is that if your atomistic code has super fast timescales, then what you want to do is you can iterate that a whole bunch of times until you update up to the delta t for the continuum code. So the continuum code's delta t is based on whatever the discretized times required to resolve its dynamics, okay? But then there's no point in feeding anything earlier because that's delta t is already small enough to resolve its dynamics. So that defines really the time scale of the information transfer. Then for the atomistic code, you can iterate a whole bunch of times until you get up to that delta t, and then average over all the stochastics before you do a passing. So, and that's another example that I'll be showing later in the presentation. So now we're ready to go into the guidelines for implementation. Now, let me see how we're doing on time. So we've got, so it's about 10 o'clock. Are there any questions now before I start going into the guidelines? Go ahead.
So one of the general issues is that to go from one scale to the other, the effort, needed in wall clock time, for example, is very different. For example, if you want to develop some potential field from QM, that can be really used in MN and D. It takes a long time. So the coupling is kind of disconnected.
Oh, no, I understand exactly what you're saying.
So it takes months before you can actually verify that some potential field is really usable in an MD simulation.
Right.
So you cannot really start an MD simulation and say, okay, I'll go develop this potential field on the fly. It doesn't work like that.
No, that's right.
So they're essentially disconnected at this point.
Yeah, I can talk about that. So there's a lot of papers on that were developed about 10 years ago. So one of it is time of flight, which is what you mentioned has problems. So what you do is, let's say you're doing MD, you can say, oh, well, I'll just call the quantum calculation for exactly the configuration I'm in, right? So it'll be exactly the system I have. I could call it, get an updated potential field based on that, and then I don't have to parameterize all the potential fields. I only have to parameterize the ones that I follow. But the problem you run into, like Sudhakar mentioned, is that the problem is it takes too long to run a quantum run. So what some people propose to do was that you run a bunch of quantum runs. You don't see the possible configurations are huge, especially if you're trying to do more larger scale kind of more accurate sorts of things involving angles and so forth. So what you do is you go ahead and you run a whole bunch of them, then you parameterize it, and then what you do is you just have something that measures in MD some configuration sort of how close are you to having a good potential field in this particular range that you're at. And if you feel that you're in a region where it's not very good, then you only rarely do runs. You only do runs when you need to do runs. So there's papers on that. And then, of course, there's papers where what you do is you just parameterize everything and then just call it dead, right? So there's a whole bunch of algorithms that go from time of flight, where you compute as needed, to compute everything before, to somewhere in between where you have a lot of it computed before and then some of it's being updated. And then as you do an update, you then improve your parameterization. Does that make sense? You follow? So there's a whole series of papers that represent the spectrum between everything pre-computed to nothing pre-computed. So now when you're doing it, one of the things you are mentioning is that when you formulate a multi-scale simulation code, you want to think, of course, like you do with any kind of parallel type computation, exactly what is the best way to do your resolutions. So let me give you an example. If I'm going to couple two multi-scale codes, and let's say one is, we'll just say code 1 and code 2. Let's say code 1 takes 99% of the time. Okay, so almost all the time is taken in code 1. So we're going to run these two codes. Code 1 takes 99% of the time. And I've got code 2 that's very, very, very fast. And now what we do is you do a delta t forward, and now you do a coupling between the two. So you pass boundary conditions, and then you step, and you step, you step. That's not going to be a very good way of using the resources, right? Because what will happen is that other code that's on the processor isn't doing anything hardly. It's done almost away, and then it just waits and pauses. So what you'll do is that typically multi-scale simulation, you're sort of pushing things enough that sort of any improvement in spatial resolution is a good thing. So what you'll do is you'll take the fast code and you'll bump up its resolution so that its approximate cost of computation is the same as the slow code. You're basically getting that resolution for free. It's not costing you any more money, right? So you might as well pump that resolution up. And so we did that repeatedly, so in our group. Another trick we would do is that we'd have not enough computations to deal with a single Monte Carlo. So what we do is we do patches of Monte Carlo. So you do a whole bunch of Monte Carlos. Because the cost of that was very high, we would then make that run on maybe 10 different processors, and then run the continuum code on one processor. And then the KMCs were selected so that each of their costs was basically equivalent to the cost of the continuum code. Again, you're trying to not waste any of the computation. So, other questions? Or? Go ahead.
About delta t going forward. So very often we have to use very different delta t's.
Right.
In these different solutions. How would you go about yours?
Yeah. So the way we do that, actually, I'm going to talk a lot about that later here. But the way you do it is that you just iterate the fast code until you come up to the same speed as delta t needed for the other code. So it turns out that approach is actually very standard in the control theory literature. They call it multi-rate systems. It's a very standard approach. There's methods for analyzing it when it's linear. There's methods of analyzing it rigorously and so forth. Yeah. So I don't think I talk about any of the deeper theory, but you can also include all that in the numerics very easily, where you basically you take the fast code and you basically you rewrite its state as the states that it's in, and then you take all the times, stack it up basically. So all the positions at one time, then the next time, you stack it all up, and then you have the vector for the other system, and then you just treat that as all the states at the same time. And then you can do analysis of stability, numerical stability, stuff like that. So, yeah. So the control literature talks a lot about those kind of tricks, luckily. So, the control engineering literature. So now we're going to go into the guidelines. So what I'm going to do is I'm going to list each of the 5 guidelines, and then I'm going to go through and give examples, explain what the issues are, and then just walk through and discuss each of those. So. And I've seen cases where whole PhDs were almost wasted because they didn't follow one of these guidelines. So they're a bit subtle, but it turns out they make a vastly big difference when you're formulating your multi-scale simulation. And multi-scale simulation is one of those areas. I mean, this is true in computations anyway, but sometimes you could write a code for, let's say, a PDE is a good example. So you write a PDE code and you've got a mistake in it and you don't know it. Because if you have a diffusive terms tend to sort of filter out your mistakes, sort of smear it out, So if you have a big enough diffusive term, you may not see that you've got an error in your code. And I've seen this happen before. Small error, but it'll be sort of filtered out. Multi-scale codes, typically, if you have an error in the code, it doesn't filter out. It causes problems, you know. So it tends to be much. You want to be even more error averse, I guess, when it comes to these kind of codes. So I'm going to go through these guidelines. These were sort of developed over a period of about 10 years of making the mistakes usually, and then finding out what the mistake was after, you know, some time, and then realizing what the mistake is, and then writing it down so avoid it in the future. So these are basically discovered by making mistakes. That's how we found this out. So the first guideline has is to prefer conservative methods over non-conservative methods for implementation of continuum codes. Now, when I use the word conservative here, I don't mean like conservative in that it's not exact. What I mean is just that it conserves properties like mass, moles, and charge. Okay, so it's using conservative in that term. I know it's a little bit weird terminology, but this is the terminology that the numerical methods people use. So that's why we're using it. But they use the word, they call it a conservative method if it conserves mass, moles, charge. So as long as it conserves properties. And we're going to find out that there's a huge difference. If you take a conservative code and non-conservative code that simulate, that you can compare their error differences will be minuscule. But you put in a multi-scale code and you get vastly different results. Okay, and I'll explain why that is. It's kind of weird, but you can vastly magnify errors when you have a non-conservative code. The second guideline has to deal with the way you order the passing of boundary conditions. So I mentioned about this idea that you can have one code maybe have a flux, feeds to another code, and the other code provides a concentration, and you iterate. Turns out it matters the order, okay? So you might think, gosh, shouldn't it matter? No, it does matter, okay? And I'll give, at least it matters, very often it matters. And I'll give examples where that matters. You think it wouldn't matter, but it turns out it really, really can matter. So you really have to think physically about your problem and then decide the order of passing the boundary conditions between two codes. In a multi-scale simulation, you want to have, if each of the separate codes are self-consistent and have been thoroughly tested and debugged, which they should be, then your whole accuracy is, you know, this iteration of the boundary conditions. If you can get those to converge, then you've got the overall problem solved, right? You've got high accuracy. So, but there are cases in which if you choose the order incorrectly, it doesn't converge, right? So because the order is wrong, you try to do the iteration won't converge. So I'll talk a bit about that. So. Another one has to deal with how do you try to get a feeling for trade-off and accuracy versus computational expense. So you can iterate to convergence, especially if they're deterministic codes, then like I mentioned, that's easier. You can iterate convergence. Definitely that'll give you the highest accuracy. You can get whatever accuracy you get in your accuracy of the multi-scale code will equal the accuracy of the least accurate separate code. And it's pretty easy to show that. So iteration convergence is great, but it can be very expensive. Okay, so. And it's difficult to do if you're doing a Kinetic Monte Carlo or some kind of stochastic code. For the reason I said earlier, when you run the stochastic code, you get a different answer, and so you can't really converge that very easily. Like I mentioned, there's tricks to do that, but it's not easy to do. These last four are really more guidelines, more like extra tricks rather than pitfalls, I would say. So, and so one of the tricks is to use a filtering of the output of the stochastic simulation code, if you're coupling that to deterministic code. And how do you do that in a way that doesn't give you the wrong answers? So in other words, gives you answers that make sense or correct, so correct with the physics of the problem, as well as giving you numerical stability. So in other words, improve accuracy and stability by modifying the equations on purpose. So you purposely introduce a new dynamic to improve the accuracy and stability. Okay. But it turns out in stochastic codes, this is something that can be done. And I'll show examples of that. And then another more advanced technique, I'm only going to talk briefly and I'll cite, is this idea of using an overlapper or an estimator. So you put another part of the code that basically manages sort of an intermediate region between two codes. And that code handles that transition in a good way. And so I'm only going to talk a little bit about that and I'll cite something because it's kind of an advanced method. But the methods I have, 1 through 4, they're all methods that are easy to implement. If you're doing multi-scale, they're not complicated kind of methods, so they're relatively straightforward. So important, but relatively straightforward. 5 is quite a bit more sophistication required to implement. And so you wouldn't go to 5 unless you really need to be able to get to the next stage to be able to solve your particular problem. Now the examples I'm going to use, I'm going to mostly keep the examples reasonably simple. So I try to make it as simple as I could come up with so that it wouldn't depend on what the background of the person is. So to be able to understand the example. So the example I have here is our copper surface. So these are all little atoms on the surface. And this happens to be after a second of deposition at low applied potential. So the way the experiment goes is you just take a batch of copper solution with some acid, sulfuric acid, and a few additives, and you just hook it up to a battery to create a field, and you just drive the positive copper ions to a surface. When it hits the surface, it gains electrons, and it sticks to the surface, and then you've got copper film. So this is basically a copper thin, a nanometer thin layer of copper. So it's basically a copper film. In this particular example, above this finite volume code is an electrolyte, so it's water solution with a bunch of stuff in it. And then you have a KMC code, which is a stochastic simulation that's taking from the finite volume code the concentrations at the liquid interface, that affects things like absorption rates and electrochemistry, and the potential field right at the surface. And then it's going to feed a flux of all the species back to the continuum code. And so these are the direction of the boundary conditions. The particular KMC code that we implemented is sometimes called a 2+1D, sometimes it's called a solid-on-solid KMC code. And so it's a particular code in which instead of doing a 3D KMC, where we have an X, Y, Z, we have an XY, so we have a distance this way and this way, so each lattice point is an XY position, and then we have height. And so that's a way of speeding up Kinetic Monte Carlo. Instead of going in 3 spatial dimensions, you use 2 spatial dimensions of height. You do a little bit of an approximation doing that, but it isn't too bad, at least in a lot of situations. And you vastly speed the code if you only have to deal with lattices along a plane with height as opposed to doing really X, Y, Z. For example, one weakness of this is if you do X, Y, Z, you can do overhangs. Okay, you can have cases in which the copper atoms actually overhang and there's liquid underneath. But with this kind of code, you can't do that. But in this system, you don't get overhangs. So it turns out that's okay. So you do a little bit of approximation, but it isn't too bad. The particular code we did had 24 different possible actions. So those were surface diffusion, various electrochemical reactions, and various chemical surface reactions. As I mentioned before, the KMC code computes a flux. The flux is a species on the surface, passes that to a finite volume code that's simulating a liquid electrolyte, aqueous electrolyte, so right above the surface. It computes a concentration of all the species and the potential. So you're solving a electroneutrality equation. That detail's not important, but you're basically solving for the potential in the liquid phase. And that governs what the electrochemistry is going to be on the surface. And that just says what I just said. So now we have an example. Now we'll go through and explain the first guideline. So prefer a conservative method. So the method we originally did was not conservative. Okay. So we use finite difference. And that's because finite difference is what they teach all my students. I knew about finite volume methods we used in our group. I told my students to use finite volume methods, but they're all trained to do finite difference. So they did finite difference. And that's when we found out about this big issue associated with non-conservative methods. The reason is that a finite difference code approximates derivatives, but it does not force exact conservation of properties. So when you run a finite difference code, you can lose mass. You can gain mass. Okay? There's nothing in that discretization that guarantees you're going to conserve properties. And that can be a disaster when you couple that to a multiscale code. Finite volume code is designed in such a way that it exactly conserves total mass in the system, moles, or in other words, the mass of all species in the system, and charges. And so finite volume method does that. Now, I'm going to have some later slides in which I go into detail the difference between finite difference and finite volume and fix this more. But this slide is really just to give you the main idea, and then I'll go into a bit more detail so you understand exactly what I'm talking about. Now, the KMC code, it's exactly conserving mass, moles, and charges. Because you have discrete events, you just add them up. Okay. So if I deposited, 10,000 copper atoms, I know it's 10,000 copper atoms. If the charges of those are all 2 plus and multiplied by 2, I know the number of charges that went to the surface. And I know the number of electrons required to make that copper atoms. So in a KMC code, it's very easy to just sum up and add all the moles, mass, and charges that were transferred, or as well as those on the surface. So that's already a conservative method. And then we basically exactly match the fluxes. Because these are conservative methods, when I compute whatever I compute, I'm not losing moles or masses or charges in either code. So not on the surface and on the continuum. And then because I'm computing these exact values get passed up to the other code. So there's no way, if you have two codes that are conservative and you couple them, the combined has to be conservative. So if this one conserves mass, this conserves mass, put them together, it still conserves mass. So, so by doing it this way, you're guaranteed that the overall system will also be conservative. And so you get exact conservation of mass, moles, and charges in the system. And this leads to a much more numerically stable and accurate code. You can imagine why that is. So if you conserve exactly things like mass, moles, and charges, you're putting constraints on the dynamics of the system. And one way, if you're more of a mathematician, you're saying you're projecting onto a lower dimensional manifold. Would be a fancy way of saying it. But what you're doing is by putting those constraints, it makes it much less likely you can go numerically stable. Because if you're going to numerically unstable, because if you're going to go numerically unstable, you have to do it in a way while staying in this manifold, while satisfying these constraints. Would be a simple way of putting it. And so that's going to be much more difficult than if it's non-conservative. Non-conservative can go off wherever. Okay, there's no constraint forcing it to satisfy certain inequalities or certain lower-level differential equations. And so that's basically the principle. What I'm going to do now is I'm just going to walk through this in much more detail to really fix exactly what the ideas are, especially for people who are not so familiar with the differences between finite difference and finite volume codes. So what I have here is exactly the same system. This is where our surface reaction is occurring, where it's going to use to compute our flux boundary condition. And so I got a color, roughly copper colored, because we're depositing copper. And then I have blue because, you know, copper under certain ionization state looks blue. Okay. And then we have a finite difference code here. And its job is to calculate, so its upper boundary condition, we've assumed in this simulation, is a bulk concentration. So there's some higher liquid that's well mixed above it that's fixing this concentration here. And then what we have here is that this code is computing what the flux is. And that flux is being fed to this continuum code. And then this code will compute a concentration and a potential, which will be fed back. So what I'm going to do is I'm going to focus really just on this part now. So the fact that I'm going to be computing a flux, which sets a boundary condition here. And I write it just as J reaction, but in reality, this is going to be all of the fluxes of all the species that's coming in. Just sort of it's just a simplified nomenclature, just to represent that these are all happening on surfaces. Okay. But there aren't necessarily really reactions. They could just be absorption. So something could just absorb on a surface. That's counted in these fluxes. And then what I have here is described sort of simply what you would do if you were doing a finite difference discretization. So each of these lines correspond to the boundary elements. So in finite differences, you'd put an element right here at the surface, the solid-liquid interface. Here, 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 right here. And that's the way finite difference goes. And then what you do is you write a PD and then you just approximate derivatives. Finite volume code is different. So in a finite volume code, you define everything as volumes. And so your center of the volumes is actually shifted. And so you're not looking at the boundaries, you're looking at each of these volumes. And then this one, you use the boundaries to tell you fluxes between each of the domains. And this one, you're just discretizing a PD. So this is a very different way of formulating things. And so this way, you just write a finite volume, and then you're just going to write this just as though it's just some volume. And you're just going to write the equations for that volume. You're not going to start off with a high-order PD and discretize. Instead, you're just going to write the differential equations directly for that volume. And that will automatically give you a lower dimensional PDE. So, because you won't have a derivative with respect to this height direction, which we'll call x. So, and so that's really the difference between finite volume. Now, what you compute in finite volume is different. Even though there's a dot in the center, you're not actually computing the concentration in the center. In finite volume, you calculate the average concentration in the domain. The center is just used as a way to sort of tag where we are. So, but what you're really computing is an average concentration within each of these cells. So this sort of puts it a little bit more detail. So if you go ahead and write an intermediate thing, you find out that the equations look very, very similar. Okay. And that's one of the reasons why it can be a little confusing just to read something up is that a lot of times when you're teaching this to undergraduates, they'll go, "Well, they're the same equations," you know. Many times they are. So what I'm showing you here is a second-order discretization in the x direction, which is height, and we're just doing the diffusion equation. And in this case, it turns out the second-order discretization ends up being the same in both cases. And so if you approximate this derivative, now this really should say partial. Sorry about that typo. I don't know why that says D there. It should have been partial with respect to x. Then you just do the standard second order discretization. This represents delta x quantity squared, not delta x squared. This is the standard nomenclature they use in the math literature. And then what you have is you have this n here corresponds to each of these points. So you call this, let's say, C0, or usually C0, C1, C2, C3, C4. I dropped the index on the species just because it doesn't change anything, it just makes things messier. In this case, what we're doing is when people do finite volume, they will write their indices in different ways, depending on what is simpler for what they're trying to present. So in this particular case, some of the papers when you read will call this c to the 1/2, c to the 3/2, c to the 5/2. So what they're doing is they're using the center to say this is the center of my cell. Some of them will just shift everything by 1/2 and write it as integers because that's what you're going to code. Because you aren't going to code an index that's 1/2. You don't have a c to the 1/2. You got to have integers in your vectors. And so, but in this particular case, I'm going to use the nomenclature where this corresponds to C0 and this corresponds to C0. So, and if I write it this way, it turns out if you work out all the math carefully, in this case, the way you do it is instead of discretizing, you write out the exact equation for each of these, including the averages and integrals, and then you write approximations for the flux between cells. And it turns out it'll give you the same equation. So, in this particular case. And so then you go, okay, well, they're the same. Okay, fine. Well, why should we even do it differently? But it turns out they're not the same. So for one thing, these equations are solving for the values at these interfaces between cells. This one is solving it for each of these volumes. Okay, so they're actually shifted in some sense. So this one, the center is here, and this one, it's a point location there. In this case, it's a center within a domain. So clearly, you would get an error. These wouldn't converge unless there's something different about the boundary conditions. And that's where the big difference is. So the biggest difference between finite volume and finite difference is what happens at the boundaries. And how you handle the boundaries is why you can have a self-consistent code where this is shifted by a 1/2 cell and this one isn't, because the boundary conditions are handled differently. Now, what's nice about finite volume is that each of the equations you write in these domains end up being an exact equation for the conservation equation for the moles in each domain. You can work it out, it's exact. The only approximation is how we represent the flux in between cells. Okay? That approximation is what also gives us the same error, it turns out, for finite difference in this particular case. Okay? But it's still conservative. Why is that? Each cell does not necessarily exactly conserve the mass, but the overall system still does. And the reason that is that if I write an approximate flux between these two cells, the flux that's in the equation for this one is equal to the minus of the one in this one. So when you put the cells together, those fluxes cancel when you're calculating the overall balance. So if I draw a control volume around this whole system, all of those approximate fluxes interface all cancel, so there's no error in my total overall balance of moles. So as long as I exactly represent the boundary conditions, I'll exactly represent the overall moles of the system. And so you don't conserve everything exactly in each cell because you're approximating fluxes, but you do conserve all the moles in the overall system. So that's the part of the conservative equation that's important. So in your overall code that you're doing, you want to be able to exactly conserve the properties. So now let's say about what the flux and how the flux is different. Now some of the stuff I'm going to talk about now is actually more general multiscale in the sense that this is actually an important point even if you're not doing multiscale. So I'll make the point anyway, but it's also relevant even if you're only doing a continuum code. So what I'm showing you on the left here is I'm showing you how you would represent a boundary condition, one of the standard ways of doing it. And there's a bunch of different ways of doing it, but they'll all have the same problem as this one. It's just that this particular way that I did it is easier to understand what the issue is in terms of the, if you try to use this code and couple it to another code. So if you write the flux, this is fixed law. I just discretized the fixed law. So you get minus d partial of x with c with respect to x. Plugged in the first order approximation. This is C0, this is C1. You can resolve this and get this equation. Now it turns out there's a big deal here, okay? So what is the big deal? At first this seems totally fine, and probably all of you have implemented this many times. But it turns out this thing can be a disaster when you connect it to a multiscale simulation. But it can also be a disaster in other problems. And why is that? It has to deal with this flux term. So what happens is it's very common when you're dealing with a multi-scale system for these fluxes to become large under certain conditions. Why is that? You're typically operating under conditions that might have a pretty big range in time and length scales and magnitude. So you may have order of magnitude changes, for example, in the potential. And as you do this, this can become very large, at least for sometimes. Might be short, but for sometimes this can be very large. But if you look at what happens when this is large, when this is large and this is fixed and this is fixed, this becomes a very large number. Okay. Eventually, this number can easily become larger than the difference between these two numbers would normally be. Okay. So if you think of it from the top, if this was the bulk concentration, when you first start this thing out, if this was all uniform, this concentration would equal the bulk concentration, right? This would be fixed. Now I do my first time step. Okay. This thing has been fixed. Now I need to solve this. This becomes a large negative number. You get this minus a large negative number. This is negative now. Now you're trying to feed a negative concentration into your KMC code. KMC codes don't handle negative concentrations. Now this is more general than KMC. The reason, than multiscale. This shows up in multiscale because very often you're dealing with time and length scales and you have orders of magnitude variation. So very often you get very large fluxes. And so that's when this thing kills you. But it's also true in general. If you take any problem that involves finite difference, you run giant fluxes, you can run into this problem. You get negative concentrations, and what will show up in numerics is you'll get zigzag patterns. Okay? You'll end up getting, it has to force the C's really big, but then as it propagates in, as you move to future times, you'll get, this one has to be large negative, but to cancel, I got this one positive, negative, and you get zigzags. So you'll get in here a numerical aphysical oscillation that will just move into your continuum code. So, and so that's really what the problem is with using finite difference. One of the problems. The second problem that I already mentioned is that if you use finite difference, it's not conservative. So if you couple it in, you can also sort of bleed out mass. And I've seen people do that. There are published papers, including an award-winning paper in the literature, that loses mass. If you carefully look at it, they lose about 20% of the mass, okay? Because they weren't using a conservative. They were using finite difference, and they were slowly bleeding mass. They got a little bit of extra errors due to the way the boundary conditions were handled. And over time, you didn't really notice it. But if you actually look at the end, it's 20% off. They lost 20% of the mass. So it's one of those things that's more likely to be induced by multiscale because if you're coupling to stochastics and other things, you can introduce larger errors because your finite difference code is assuming sort of a certain level of smoothness that doesn't exist in the boundary anymore. So the errors can get bigger than you think they are, and those things can integrate over time. So, but this is another sort of issue. You can induce a numerical instability. Now, if you look at the way a finite volume code, it doesn't have that problem. So the way a finite volume code is that you write down here your equation, and then what you've got is that you need to represent the fluxes. That's going to give you the ins and the outs when you write down a finite volume expression here. But this particular flux, you're actually given by the KMC code. So you just feed the flux right into the equation. So if you write it out, this is the equation here. Now I'm going to use the nomenclature where I use halves, because I usually prefer to use that nomenclature. So I'm going to call this c to the 1/2 instead of c0. So if you take this particular point, I can write down a conservation equation. This c to the 1/2 isn't really c to the 1/2. It's the average concentration within the cell centered at 1/2. Okay, I could have put a hat there to make that clear. And then you can write that down just as an ODE system. You've got, this is only 1D, so instead of writing delta V times A times delta X, I just called it delta X. I just divided through by delta X. So this is basically the amount of moles in that particular cell, just divided by the area. This is the term associated with the flux that would be coming in across here. And then this is corresponding to the exact flux here. So what you can do is you can feed your flux exactly in a finite volume code that occurs at a boundary. So any boundary flux is exact in a finite volume code. In a finite difference code, it's always an approximation. So, and so again, it's good to have that, right? It's good to have this, this property. In this case, it turns out you don't run into this numerical instability because this is a time-varying equation. You can just always, as long as you use an adaptive time stepper, which you would always use, at least I would normally use adaptive time stepper because it's a lot more efficient, then it'll just shrink the delta t naturally so you don't run into those oscillations. Oscillations go away. So it has that degree of freedom associated with time it can use that the adaptive time stepper can just keep reducing until everything's fine. Whereas the finite difference code, it doesn't do that. So if you look at the left-hand side, there is no time here. So adaptive time stepping, whatever, doesn't help you here. You shrink the delta time, whatever, you still get the same oscillation. So So to sort of summarize, so finite volume method exactly conserves mass, moles, charges. The conservation constraints lead to more robust code linkages. What I'm going to show now is I'm going to do a very specific numerical example to illustrate. And it'll show you exactly the phenomena we were talking about. So what I have here is I have that simple example. And in this particular case, I have one particular parameter. And we've actually, I think this, if I remember correctly, I think we've simplified this to be just like one reaction, relatively simple. And that reaction here happened to be, if it's relatively small, what you're showing you here is, actually, is this multiscale or not? Actually, I don't even think this is multiscale. I think we did this without doing multiscale. So this was just doing just the finite difference of finite volume by itself. And then we had the surface on the bottom where we just assumed it was just a continuum reaction occurring at the lower part for the copper. And that way we don't have any convolution associated with the KMC code. We're looking just at the finite difference of finite volume and see what happens there. And in general, when you're doing multiscale, you really want to make sure that each of those pieces are really robust and really reliable. That actually leads to another point. When you look for the reliability of a code within a multiscale code, typically the reliability needs to be much higher in terms of a much wider range of operation. Because a multiscale code can take you off into places typically farther than you normally would do in a regular simulation. So for example, if I'm doing a simulation of, let's say, diffusion, I would already know a lot about the solution. You know, I know it might have to be monotonic and so forth. So then I can develop a code that maybe is really well tuned for that and fast for that particular range, but may not be good at other ranges. But in a multiscale code, typically you've got orders of magnitude variations in your system. So now you need a code that's really robust, you know, for all of these variations. So you really need to test and make sure you have a, you know, numerically robust code over a wide range before you put it into a multiscale coupling. But in this particular case, what we've done is we've treated it, so we treated this as just a simplified version. If the reaction ended up being sufficiently slow on the surface, which corresponded to a low flux, so if you have a low reaction, it won't be sucking much material out of the liquid phase, then both codes work fine, and you get the same answer. But when the flux got a little bit higher, you can see it's not much, right? So we're just changing the flux. This will be translated into the flux, because the flux has to equal the chemical reaction on the surface in this example. We just doubled the flux. And in this case, finite volume, everything's fine. No problem. You go to finite difference, and you can see this is 10 to the 4th. This is 10. So in 10 to the minus 5 seconds, changing the flux by a factor 2 created. Now if you zoom in, you actually get, so the zigzags in space also got translated eventually into zigzags in time. So basically induced numerical instability in time. And so you can see how big it was getting. So, and this is a very simple example. That's just the diffusion equation, and it just used the reaction on the surface was just K reaction times the concentration at the interface. Very, very simple. You can clearly see the problem. So you can do this at home. It takes about 10 minutes to code this up. So we're not a big fan of finite difference codes in the group. And it also explains why if you look at the big fluid dynamics codes, they don't use finite difference anymore. They all switched to finite volume about 10 years ago. So for these kind of reasons. Are there any questions about the first consideration? So it's a great example where you can do everything right, or think it's right. You know, finite difference. You know, you do all the error analysis. All looks great. You know, then you run into multiscale code. It increases the flux a little bit higher than you saw before, factor 2 more. Doesn't seem like much, and then bam, your code's unstable. And in a multiscale code, it's harder because the whole multiscale code goes unstable. You don't know why. What caused it? You know, what was the issue? You may not have realized that it was because you used a finite difference code and you had larger fluxes. So what I'll do now is I'll cover the second one. Well, let's see how we're doing on time. So right now it's about 10:30. People want like a break, like a 10-minute break, or are we going strong? Or raise your hand if you want to have a break. Okay, a couple people want a break. How about if we take like 5 minutes off, or 5 minutes, 10 minutes? So raise your hand for 5 minutes. Okay, raise your hand for 10 minutes. Okay, we'll go for 10 minutes. So we'll go for a 10-minute break, and then I'll go through the second one. So the second gotcha. So the second guideline. Now the second guideline is I think is quite interesting. This was a case in which I learned about this because I inherited a multiscale code from somebody else. And I just was asking questions. And then later on, it sort of guided me into this, and then we reformulated everything to switch the boundary conditions. And this is a kind of subtle. It's not the kind. It's a kind of error that'd be pretty easy to make. That it's not obvious why it would cause big problems. And to understand this, it really helps if you think like a physics person or engineer, and less like just a numerical person, to understand what's going on. So if you remember, we've got our Kinetic Monte Carlo code that's coupled to a finite volume code for bulk electrolyte. The rates of so again, I'm just going to go through this example, and then I'll go into detail about the specific guideline, and with an example about what happens if you don't violate it. So if you're doing a formulation for this particular problem, this particular case in which I put the flux and the concentration, this was not the way it was originally done when I inherited the code. So, and then we reformulated to do it this way. And so what happens here is that there's a bunch of heterogeneous reactions. In other words, reactions on solid interfaces, in this case a solid surface. And these reactions depend on the concentration in the electrolyte phase, so the aqueous phase above it. And so you can imagine if you double the concentration, for example, in the aqueous phase, you'll double the absorption rate, for example. So all the electrochemical reactions that involve species that directly react with solution will be approximately doubled will be doubled when you double the concentration at the surface. This is all assuming elementary chemical reaction kinetics expressions. And so this is clearly one thing that we do. The fluxes that are computed, those are computed in a KMC code based on these concentrations, because the concentrations go into the transition probabilities. So each of the transition rates, each of the transition rates are a function of the chemical rates. And so the chemical rates are a function of the concentrations above the surface. So concentrations goes into the rate of reactions, which goes into the transition rates, into your KMC code. So that's how the information is passed to the KMC code. In the KMC code, they can then compute fluxes, and that's based on the reaction rates that occur here. So some of these reaction rates will deplete species that are in solution, and some will actually put species back into solution. Now, the thing about this particular coupling, if you think about this order of coupling, it makes physical sense. So if you have a surface here, if you think just from a chemical point of view, if you're sitting here on the surface, if I double the amount of species above the solution, that should double the rates. It's very easy to get access to molecules that are on the surface. And so it's very natural from a chemistry or physical chemistry point of view to think of this being driven really by these concentrations. It's really a function of those concentrations. Similarly, the electrochemical reactions are a function very strongly of the potential. If you change the potential, you can basically switch on or switch off the chemical reactions. So this directly feeds into chemical reactions, which directly feeds into the transition rates in the KMC. So from a physical chemistry point of view, this is the information transfer that makes sense. What is happening in the liquid phase, or the aqueous phase, the electrolyte phase, is directly influencing what goes directly into the KMC code. So this is really consistent with physical chemistry. And then whatever occurs on the surface, whatever these reactions are, they're going to have depletion on the electrolyte phase, or they're going to add materials to the electrolyte phase. And that is a flux. And so this is the natural way of connecting the boundary condition. So I inherited this problem to switch the other way. So the flux was coming down and the concentration was going up. And that's what caused the problem. Because if you think about it, the electrolyte phase, it can't specify fluxes. So if you're a liquid phase material, that's not the boundary. That's the bulk. It's a bunch of liquid above it. And so liquid that's sitting up above cannot specify boundary conditions on fluxes, because it doesn't control the fluxes. If I change the surface, I change the flux, on the surface. So switching it the other way is sort of trying to put information sort of not in the right order. Now, it turns out that I got in a big disagreement with a famous professor about this particular ordering. Okay, so he said it should be the other way. He's the guy that wrote the previous code. But it turns out he was right, sort of. He worked in the field of physical vapor deposition. And he had already done a lot of multiscale simulations. And when he had done it, he had always done the fluxes down and the concentrations up. Okay? But in physical vapor deposition, that makes sense. So in his case, he's bombarding the surface with particles. In that case, the flux of particles to the surface is specified by whatever he's using to bombard particles. It's not specified by the surface. He's physically forcing particles down. So in his way, it made perfectly sense to be having the bulk phase, or the phase above the solid, specifying fluxes to the surface, because that's what's governing the fluxes. That's what's specifying the fluxes. So if he puts in a higher charge ring to put, particles, ions, closer to the surface faster, he directly specifies the flux. So he was right for physical vapor deposition, but then he tried to transfer it into this, and then that's where he ran into problems. So. And so this is really the way to think about this. So what I'm going to do again is I'm going to give you a very specific example. So we'll just walk through an example. It still will be chosen reasonably simply. So here we're going to use a trench. So I talked about this example. So this has been etched out. In reality, this is going very, very long. But of course, if I draw it all the way long, then it's kind of hard to see what's going on. So I've just shown it as just being a thin slice. And so we have a trench here. It's going in and out of the paper. Inside here we have, of the screen, we have a 2D transport. And then we also have 2D transport here. So this could be convection, could be diffusion. Definitely diffusion is going to be happening. Under certain conditions, you need to model convection. In certain conditions, you don't. And if you go far enough away, there might be a whole bunch of these side by side. I haven't drawn this to scale. These are actually, tens of nanometers, so actually quite small. Tens to maybe 100 nanometers. And you've got a whole bunch of these. So you go far enough away, it basically looks like one-dimensional transport. And then we have, so you might want to write a code here, maybe a code here, and maybe a code here. And then information must be passed between these if you're going to be able to simulate the overall system. And then we have a choice about whether we choose concentration or flux specified by, let's say, I could have concentration specified by here, or I could have concentration specified by here. Wherever I specify concentration, I get the flux coming in from the other direction. So concentration is specified here, flux is specified here, and vice versa. And then they compute, and then they pass information to the other direction. What I'm going to do actually is I'm going to consider the very simplest case to illustrate. So we're going to assume all the codes are just 1D. So we'll just have both codes, there's 1D. And that way we can draw something very similar to what we just had in our previous example. So it's very simple, so we can just illustrate everything. And so what we have here again is our bulk boundary conditions. So this is very high up, and it's in a larger, well-mixed domain, so it really is fixed. We have our surface reaction occurring down here. And we have two choices. So we can either have a higher domain specifying the concentration, and have the flux specified by the lower domain, the lower cell. And again, we're only going to use finite volume here, because we know from the previous guideline we should only use finite volume. In this case, we'll have the flux specified here, and we'll have the concentration specified here. And again, we'll have a very, very simple reaction listed here. And then we'll just do the simulations. This is 1D, you can easily do it at home, so it wouldn't take very long to implement. We already went through the equations. So the equations here in the bulk phase is just given by this, which was derived by deriving an exact equation for each domain, but then approximating the fluxes in between each of these cells. If we go down to this particular boundary condition, we can write out that boundary condition. And this basically just is associated again with reactions that's occurring on the surface and transport associated with diffusion towards that surface. I won't derive it here, but I can derive it offline. It's not totally messy, but it takes a little bit of time. And then the question is what happens at the boundaries? If I was going to do a code in blue, for example, it's one continuum code, another code in white. So these would be, let's say, outside the trench and inside the trench. How should I do this? Should it be this way or should it be this way? And this, of course, the inside part doesn't really matter from a multiscale point of view. So multiscale point of view, we're looking at the interfaces between the codes. And the determination of how this is solved, presumably this is all solved simultaneously anyway. So we're only asking the question about information passing between one code here and one code here. Now, even though and then this reaction code here is going to be the same boundary condition. So what we're doing here is that the bottom codes are exactly the same in both cases. The top codes are exactly the same. And both of those codes are simultaneous, so they solve all the equations at once. So the only place in which we're going to do passing is right at this interface. Okay? Now what's interesting is I'm not talking about different boundary conditions. So we know the boundary conditions here because they're specified by finite volume. So we're going to ask the question does it matter, even away from an interface, does it matter about which is the order you specify? In other words, is the flux specified by the top code or the bottom code? And what's interesting about this is we're not even close to where the actual reaction's occurring. We're actually somewhere here in the bulk. So you would think it doesn't matter. I'm far away from the surface. This is a simultaneous code. It's the same in both cases. This is the same, that's the same, that's the same, that's the same. If you're far away from the surface, why would it matter? You would think it wouldn't matter. So we'll find out it does matter. Conservation occurs at the surface. Flux directly depend on rates of reactions on the surface. So the surface is really what specifies the flux. You can try to switch directions, but in some sense you're putting the cart before the horse. So at least that argument is certainly true here, where the surface is specifying the flux. So what I'm showing you here is exactly the same two systems in terms of the top code and the bottom code. And they're both simultaneous codes, finite volume codes. And what we're showing you here is different cells. So we just have 6 cells. And this is showing, in this case, I've actually labeled them. So basically, the ones that are labeled as flux passed down are the blue ones. And the ones that are basically dark are both the exact solution and the flux passed up solution. And these were computed exactly the same discretization. So it's a discretization of 6 in both domains. And what you can see is that there's a gigantic difference. So whenever you pass this blue, the flux passed down, the flux going down, which is aphysical, it's not physical, you get very, very large errors. Okay? If you have the flux going up, which is physical with the boundary condition at the bottom, then you get almost no errors. So, and so even though it's not even close to the surface, I mean, it's kind of, maybe it should be a bit surprising, even though this code's exactly the same as this code's exactly the same as this code, and we're far away from this interface of specifying the flux, it's still important to specify the flux so that the flux is going, is specified by the bottom surface here and specified by the lower surface up. So you want to have that interface still consistent. The direction of information passing there should be consistent with the information passing here. So, and so that very subtle change, you know, makes a huge difference in terms of accuracy of the code. Are there any questions about this? So it's a bit subtle, but you don't have to necessarily be right at a boundary condition to really think about what is the proper way to transfer information. Now, if we iterated, now the particular algorithm I talked about is a case in which we've just done passing once. So we're just passing and going forward. Now, of course, if I iterate them to convergence, then it doesn't matter anymore, right? Because then you're iterating back and forth until you converge the concentration and flux to the exact, you know, within 10 to the minus 8th at the interface. Then it doesn't matter. But if you're not converging all the way, so iterating until all the equations are the same on both sides, if you're doing this, run a code and then pass boundary condition, run a code, pass boundary condition, that's when you get these big, big differences. So, so when you're solving numerics, you shouldn't throw away the problem. So think about the problem too. So the first 2 examples I gave were somewhat subtle. This third one is guidelines, but I would say that the information I'm going to give you is probably enough that you can use that to sort of guide how you design your code. But I think it's a little bit less subtle. So, so if you try to do analysis or uncertainty analysis with multiscale codes, it's difficult. If you have a stochastic code and you're coupling that to a continuum code, that ends up being pretty darn complicated because if you think about it, that KMC code, if you're doing it to compute some boundary condition and passing it to a continuum code, you're feeding all this noise to the continuum code, okay? And the thing is that the continuum code is not designed to handle that, right? So the continuum code has assumed certain amounts of differentiability. And actually higher order accuracy in the deterministic code can cause problems, right? Because it's assuming implicitly a higher order level of differentiability, okay? So if you have low differentiability because you're putting a bunch of noise, then that's actually worse. You're actually so much better doing first order in time other than higher order in time, for example. So, so the thing is that it's inherently difficult. The other thing too is that when you're dealing with complicated systems like PDAEs and PDEs, you've got just trying to put that into some analysis framework when you've got 2 million or 2 billion PD, you discretize get 2 billion ODs that are highly nonlinear. Generally, analysis of nonlinear systems in general is not an easy thing anyway. So what we have here is I'm going to talk here about information analysis, and I'm not going to show you the details of the mathematics. But the rules and stuff I'll tell you, because those are really what's valuable when you're implementing a code. So what I'm showing you here is a very generic representation for a simple multiscale code. So we have code 1 up here, and so this is described by, could be PDEs, could be ODs, whatever. But I discretize all the space variables, so I do some sort of basis function expansion. And so now I've got it down to some kind of ODs. And typically in practice, when you do problems, you usually don't discretize all the way to algebra. So really, even though you're taught that as an undergraduate, that's usually not a very good approach. At least it's a very bad approach for chemical systems. Anytime you have chemical or electrochemical, you only want to discretize the spatial variables. And the reason is because in chemical, electrochemical systems are extremely stiff with ranges of timescales, often like 10 to the 18th. So if you try to discretize all the way, you'll end up getting very, very slow inefficiency because you have to use really tiny delta t everywhere. So what you do is you do to ODs and you use an adaptive time stepper, and then it'll shrink the delta t when it needs to and be really big when it can. And so that'll be like many, many orders of magnitude faster. So as I typically, when you write it down, you really get something that looks like this. And then you've got some sort of boundary condition. So what I've done here is X refers to the states. They could be compositions, temperatures, whatever you have in this code. And you just stack it in a big long vector. And then you've got this big long vector. And then it has an input, which is a boundary condition coming in from this other code. So they call that squiggle. And then we have time. And then this EI is just so it can also handle algebraic equations. So electrochemical systems, for example, have algebra as well as differential equations. And so you can use a rank deficient matrix here to deal with the algebraic equations. And so you can think of this as just a nonlinear dynamical system with some kind of output, which is its boundary condition, that's then passed to the other code. And then you can see here, y are all the states of this code. And then it's got its input boundary condition came from here. And then it's a function of time. And it could also have algebraic equations. And then it feeds an output, which is squiggle, which goes back into code 1. And so one of the things that we did this maybe, I don't know, 10 years ago or so. So to deal with trying to do the analysis, you can understand a lot of the issues with multiscale codes in terms of numerical stability and numerical accuracy, as well as computational expense, just by treating it just in this very simple way. So you could argue, for example, that the KMC code is some sort of base behavior, an expected value behavior, or nominal behavior, plus some noise. So you can just add some noise to this. And I'll talk a little bit about this later if I have time, where you can basically explicitly add noise to this. And just for analysis terms, can you sort of argue about what is the order of accuracy and what's its trade-off with computational expense? And so that's what this slide does. So you can walk through the numerical analysis pretty easily for the equations that I just showed. And the reason you can is because numerical analysis has been pretty well developed for differential algebraic equations and ordinary differential equations. And so you use the same exact techniques you'd use for analysis of any OD or DAE. You just have two sets of equations, but you just write those two equations side by side. So if you look here, you can now write a new vector that involves x and y as states. And then you can just stack all this up as a new DAE. And now you can just do standard numerical analysis on that DAE. So it's basically a structured differential algebraic equation. So you pick up a book like by Linda Petzold, or it'd probably be a good book. But you can also have some other books on that subject. And then it'll walk through how you do numerical analysis. And they do some tricks, right? So they're doing things like linearizations and stuff to allow them to do order accuracy estimates. But if you do that, you can work out this plot that I show here. So you can plot numerical accuracy here, and you can do computational expense. Now the accuracy I'm referring to here is accuracy in time. I'm not talking about accuracy in space. I've assumed that each of those individual codes, well, not even an assumption, each of those individual codes have been resolved to whatever the spatial resolution is for them anyway, okay? So what I'm worried about is what's going on at these interfaces between the codes. And then what is the limitation in the overall numerical accuracy in time when you couple two codes, okay? So what we're showing you here is this first approach here is the direct coupling approach. And what you can prove is that it's first order accurate. That's a case in which you have two codes that are running in parallel, so code 1 and code 2. And then what you do is what you pass is, let's say, the boundary condition, let's say for k plus 1 is used in this code was from k from the previous code. Okay? So you're always basically off on the boundary condition by delta t potentially. Okay? And it's not a big surprise if you think about it. It's not so different from the Euler method or the Euler method, so EULE. So the math is very similar, and you can show that you get first order accurate, just like you would for an Euler method. And so it's not too hard to show. And so that tells you that you've got something that's clearly the fastest, because your speed is just the time required to basically run the codes separately. Little bit for coupling, but not much. But it's only first order accurate in time. If this individual codes were, let's say, third order accurate in time, it wouldn't matter. If you do this coupling, the overall coupling is first order in time. Okay, so now if these are already first order in time, maybe that's not a big deal, right? They're both ordered already, okay, it's still first order in time. You don't really lose much. So now if you use a predictor corrector like algorithm, just like you would for ODEs, you can show you get second order accurate, just like you do for ODEs. So it's not a big surprise there. Predictor corrector is where you basically project forward and then use that to do a correction and then you resolve. So it requires 2 solves. So it's going to cost you twice the expense roughly, okay? But you're going to be able to bump it up to second order accurate in time. Now you can also iterate to convergence. So iterating convergence is where at each time you iterate until you converge to a self-consistent boundary conditions between the interface. And I'll show some examples. I'm going to show examples of all this shortly. Okay, so I'll just like talk about the concepts and I'll do the examples. So, and this can cost you up to 3 to 20 times or so. Of course, it's going to depend. It's very similar if you do an implicit method anyway. So if you do an implicit method for solving ODs, very often it takes 3 to 20 iterations within each of your iterates. So what you do is you write an implicit ODs when you do the discretization. You get a set of nonlinear algebraic equations. You then solve that simultaneously. But you can warm start it with the information you had in the past time. So you can usually get it down to 3 to 20 iterations based on how you chose your delta t. So this kind of thinking, this kind of estimate is very consistent with any implicit solver for ODEs. And so you can, again, use that information for ODEs and DAEs, what's known about them, to sort of interpret what happens if you do a multiscale simulation. And so that's basically what this just says. So you can use the numerical analysis for ODs and DAEs, such as in Linda Petzold's books, but also elsewhere. I love listing her books because her books are very easy to follow and very easy to understand with basically minimal math background. And you use this to gain insights into numerical accuracy and the trade-off between accuracy and computational expense. Because basically you can treat it as though these are the systems plus you've got some noise. Now you can say, is this like a rigorous proof? No, it's not. Rigorous proofs are very difficult in this field. But this is very, very useful guidance. Okay, so now I'm going to go through an example application. Now this particular application I'm going to use a little bit different than the past one. This one happens to be some simulations that we did with Richard Alkire's group at Illinois. Here we have a diagram. This actually, I'm pretty sure this was actually an AFM image of a pit that's been corroded in stainless steel. And so stainless steel has these various inclusions, including Mn sulfides. And these are used to make the material have its nice mechanical properties. But on the other hand, when you have pitting, the pitting tends to happen at these inclusions. So now we have some sort of acid that's coming in here and it's sort of eating around this inclusion. And so the idea is to simulate this particular process. So I'm showing you here what the simulations were. So we've a little bit idealized. So we have some kind of wall shown here, and then we have the stainless steel. And there's a bulk concentration out here, and we assume just symmetry. And so here we have stainless steel wall. Here's where the inclusion is. We're basically simulating right at the crack. So right at the crack in between, where you've got Nn sulfur, which is this inclusion. Then you have this little crevice, and then you have stainless steel on the other side. So it's an idealization because this real sort of channel doesn't really look like a rectangle. But this is a reasonable approximation to at least gain some insights into what's going on. So the micro crevice model was a 2-dimensional. It used an implicit Euler, sometimes used predictor corrector, so it depended. All the equations, they were written as implicit. They're written as nonlinear algebraic equations, and that's great for running PETSI. So PETSI is a very well-known parallel numerical linear algebra solver that you can run on supercomputers. It was developed at Wisconsin, but very, very, very nice piece of code. And so that was all done, so we do it in parallel. And then you can also write down equations, an alternative implementation. We did a later implementation that was also 2-dimensional, but in that case, instead of using an implicit with PETSI, we ran it through DASPK. And DASPK is a very well-known DAE solver. And this is an electrochemical system, so you get algebraic equations you have to solve. So that's why we need the algebra part. And then what's nice about this is it has built-in sensitivity calculations. And so it'll calculate sensitivities with respect to parameters not for free, but for pretty cheap. And you don't have to do any coding for it. It's all embedded into the code. So this is very nice. We use typically for analysis, and this is used for like large scale runs. You know, we're not doing analysis, we just want answers, like parameter space. You know, change parameters, how does it change the answer? In this case, we can do analysis like what's the effect of the states by changing various parameters in the model. Now the coupling between them was to pass the potential fluxes and concentration between the codes. So very similar to examples I had earlier. And then in the bulk and crevice, this larger part out here, so above this little rectangle, this larger region, that was always used this way. So, and that's because all the interesting stuff was happening in the trench. So we cared about doing sensitivities down here, but we didn't care about doing it up there. So no interesting chemistry was occurring. So what I'm showing you now is the simulations for that particular coupling. So we have two continuum codes, one at very tiny length scales and one at much, much bigger length scales. And we're just coupling here. A monolithic code means we solve it all at once. So we just solve all the equations of the little tiny crevice and in the bulk at the same time. And that's shown by this black line here, these black lines. And then what I'm showing you here are different important species or important states. So we have a potential is very important because the potential really affects the electrochemical rate huge because it goes into an exponent. We have pH, which is the amount of proton concentrations lying around. We've got one of these sulfur groups, so S2O3 ion groups. And this is in there. That's when the sulfur becomes into the liquid phase, and that's bouncing around the liquid phase. And then we have chloride ion. And what you can see is here's the coupled code. And so what we did here was we ran it under the high speed, low accuracy. So this is a case in which you were just doing direct coupling. So you have the two codes, they're running in parallel. They do a simulation based on the boundary condition for k plus 1s based on k. So you just keep stepping it forward. And if you do that, what you find out is that some of it's not too bad, but the potential's off pretty, by huge amounts. Okay. So it really doesn't get the potential very good at all. And it doesn't get this very all. But it's fast. Okay. We only call each code for each coupling time interval, so it's cheap. But the errors are pretty large, pretty substantial. Now this shows the alternative extreme. So this is a case in which we ran the two codes as separate codes, but we iterated the boundary conditions. And so you just keep feeding them between the two codes until it converged to consistent boundary conditions. So that what is in the codes for the fluxes of both codes and the concentrations is exactly the same. Now, of course, once you've done that, the accuracy is the same as if you just solved it all at once. So it's the same as the monolithic code. Okay, so now you've got exactly the accuracy of solving it all at once. What this is plotting is since the accuracy is the same as the monolithic code where you solve everything, what I'm plotting you here is how many iterates there are convergence, because that's the speed part. Yeah? And what we did is we went ahead and did our best job of doing warm stars, using the same kind of ideas you'd use in an implicit ODE solver. And so what I'm showing you here is the number of iterates that were required for each code. In this particular case, we allowed, let's see if I remember how we did this. Right. So what we did is that the student was a bit savvy. Instead of iterating them at the same time, he would iterate the bulk until he got something and then iterate the crevice. So he basically was able to do the iterates separately because he knows that the crevice didn't change as much as the bulk changed. And so this is showing the total number of iterates for the two codes. The bulk code is what had to iterate a lot, is what you can see. And so some of the iterates he needed was on the order of 22 or 23, 22 iterates to reach convergence into a self-consistent boundary condition. I'm sort of not showing you the details, so I'm not showing the details about how he did the microcrevice separately. But the gist of it is he just didn't update it as much. And then he'd iterate the upper one so it'd be self-consistent nonlinear equations in the top code or the bulk code. So we had this period in which it ended up a lot of stuff happened. And this happens a lot when you're doing implicit solvers. So this is sort of standard. So we had a lot of iterations. And then as a steady state, if you keep running this out, it ends up being about 2 to 3 for the rest of the time. So, and that's pretty common. You get a lot of dynamics, lots of changes short. Then you get a lot of iterates to get convergence of the equations, implicit equations. But then you have less. And this just shows you that the residuals were driven down in all these to be very, very small. So, and so this shows that, yes, these iterates were enough to get very small residuals. And so by solving it all the way, the cost now is 22 to 3. It's somewhere between about 2 to 3 to about 20 or so cost increase to go from running as multi-scale code to go from here to here. So this particular one was the low accuracy, high speed. It only caused 1 call per code. This one cost up to 22 calls per code. But you get the right answer. So, so you can see what the trade-off is. And this pretty much just says the same thing. So very small residuals were obtained with 2 to 22 iterations. Results were indistinguishable from monolithic code. So, but you ended up costing 2 to 22 times instead of just 1. So are there any questions about that? So this example sort of still follows that same kind of idea, that same kind of theme, in the sense that these kind of plots I'm showing here are very similar to what you'd see for any implicit solver. You know, so when you do startup and so forth, these kind of numbers are very consistent for something that's not extremely ill-conditioned, for example. And so these kind of changes and stuff is what you would expect with an implicit solver. So that lessons you learn by looking at implicit solvers can be translated over. So what I'm going to do now is get into guideline 4. So guideline 4 has to deal with this little trick with using filters. We try in our group not to use this trick unless we have to, but sometimes we have to, just because I'm sort of a purist. But it turns out you can do a bunch of mathematics to show that this trick can actually improve both accuracy and stability at the same time. And what it does is it changes the dynamics of the system to improve accuracy and stability. So it's kind of a strange concept. But so what I'm showing you here is a much more complicated simulation. And then I'll talk about the example, and I'll describe this kind of filter directly in the context of the example, because it's much easier to understand what's going on with the filter then. So what we have here is a simulation that was done quite a long time ago, where we had a full solution of the electrolyte above a bunch of trenches. And actually, we don't solve these 3 trenches. We, of course, only solve half of a trench, and we just copied it. And so we ended up just solving one of these trenches. And we used periodic boundary conditions in this direction, in depth. So we actually only solved a very thin one, and we duplicated that this way. So it looks like a trench. So the computers were pretty slow in doing stuff. So then we went ahead and had this. Here we're doing KMC. Turns out the KMC we're doing is coarse-grained. This is the only way we can do sort of things the algebra. This particular one, if I remember right, this was actually a 3D KMC. So later on we developed the 2 plus 1 D, which is much, much faster. But this time when it was originally done, it was based on 3D. It was developed by another. But it simulated absorption, desorption on the surfaces. These little blue dots correspond to copper ions, basically, clusters of copper ions, and this corresponds to copper film. We had bulk diffusion to the film, we had surface diffusion on the surface, electrolyte surface, solid interface, chemical reactions. The time scale of the KMC goes under nanoseconds, so that was basically the update time roughly. And that's given by the rate processes that are occurring in this particular system. The length scale that was looked at was sort of on the order of 12 nanometers or so, so it's a coarse-grained code. Today, you could, of course, run much better, much higher resolution than what was listed there. In this particular case, was before we learned about the finite difference to finite volume lesson. So we learned that later. So this actually uses a finite difference code, so the finite volume code. If I was going to redo it, I would certainly use the finite volume code. And what's interesting about this is that we chose conditions. There were some weird instabilities that were occurring. And so this problem was brought to me about 2000. And what they found was when they coupled the 2 codes, they were getting instability. And so what we did is we ran it under condition, they found instability unless they ran delta T really, really tiny. Now, the way they did the coupling was to do the multi-scale simulation. They would do the boundary condition passing shown here. But what they would do is, because this time scale was nanoseconds and this was milliseconds, they would just iterate the KMC code, 1 millisecond, 2, 3, 4, 5, until they get up to a millisecond. Okay, so you run the nanosecond code a lot of times. That's 10 to the minus 9, that's 10 to the minus 3. So about 1 million times. Then you would calculate the overall flux for that overall time. So you run this about 1 million times. You calculate the flux, divide, which was what? You calculate the amount of species removed divided by time. And then you would feed that information as information would pass.
And so this kind of approach I might have mentioned is it's known in control literature as multiscale. It's a very old approach they use to control systems of fast dynamics and slow dynamics. Then the same idea is doing the simulation. So you iterate this about a million times, then you update. And the reason that works is because the time scale is actually very slow. And so it doesn't change significantly over 1 millisecond. And so that changes so low, there's no point in trying to iterate faster. So they wanted to iterate this, in that time scale. That way they had very efficient code. The problem they found was that they had troubles doing that. They had to keep shrinking this time step. And the reason is because this instability was showing that.
And they didn't like that. It was slowing down the code to be much faster than should have been required to resolve the physics of the system.
And so here's our little picture we have up here again. What I'm doing here is I'm drawing the block diagram kind of representation that we used earlier. So this just represents the finite difference code. And it's receiving some boundary conditions that come in. And it'll compute boundary conditions that go down to this three-dimensional KMC code down here. And the interface is right above, so it's right there. So you see the interface. The 3D KMC actually goes into one of the phase ends. And then here they have another operator, which is KMC. And then they've got some sort of output you might be interested in for the KMC. In this case, they created things like service functions. So that was an output that this computed that they never fed to the function. This function is going to be very much service functions. Because the length scales of search functions are much smaller than functions, so it would be influenced by what the name was the same. And then you can think of this having other inputs such as noise.
And so that pretty much describes that, we've already talked about.
Now, this is an example where they ran it under conditions in which almost nothing should be happening, okay? And they found even if they ran under conditions in which not much should be happening, a lot happened. So what they're showing you here is this is the interface of copper ion concentration, so right at that interface. And then this here is the flux of copper crossing right at the interface between the finite difference code and the 3D KMC code. And each of these dots corresponds to one of the calculations on that. So what you can see is, and it's a huge number because remember the time scales are milliseconds, showing these dots. Okay? So every millisecond there's another dot. Now what you can see is an unbelievable amount of stochastic fluctuations. You can see that there seems to be a lot of things really near zero, right? At least down here you can really tell. Right? Here there's a lot of things that are relatively small, but you've got a whole band. And so this is kind of disturbing, okay? So the real system, they expected a small number, not far from zero. And they can do the calculation of the order of magnitude to show that that's what they should be getting. But what they're getting is something that's very, very different. Very highly corrupted by KMC limit. And you can look like KMC noise, but you can also see that it's growing, okay? So it looks like this is going to be some variance growing like an exponential instability. So this should make you worried about what's going on here. Now they could get rid of it by making ridiculously small time scales, but then they can only simulate for very much less than a second. So they know it's somehow related to temporal mismatch between a couple of codes. If they shrink the delta T small enough, the problem goes away. Okay? At least its instability goes away. And so the question is what to do about it. Now the other thing to talk about this is to talk about another gotcha. You have to be very careful. It's very easy in a multi-scale code to get much higher variance than the real variances. Okay. So why is that? So the KMC has noise, but very often when you couple it to macroscopic, it's a really tiny KMC and a big macroscopic. And the big macroscopic is much larger, there's a lot more averaging over a lot more surface. But you don't have enough KMC to simulate the whole surface, so you only simulate parts of it. But that little part will have much higher variance because it doesn't have the averaging over the whole surface. It's going to be felt by the continuum code. So then you're feeding the continuum code a bunch of this noise, extra noise. But the continuum code, it's always derived on Taylor series expansions in some sense, right? So it's assuming a certain level of differentiability. Okay, it's not a discrete stochastic continuum code. And so when it's being fed stuff it doesn't really like very much, it will behave not quite so well if you don't handle it well. But also now its output is noisy. Now you're feeding that noise back into the KMC code when you pass the boundary conditions. Now the KMC code's noisy. So now you've been doing still a bunch of extra noise in the system in a feedback loop. And if it's unstable, like this case, then the noise gets bigger and bigger and bigger. You know, so you've got a bad situation getting worse. So, and so one of the things when you couple multi-scale simulation codes is you need to, if you want to really have an idea, you really capture what you want to capture, you need to think about what's going to happen to that noise. So, is it going to get underestimated? Going to get overestimated? It's also true for coarse grain. But in coarse grain, it's more easy to figure out what's going on. But in multi-scale, you need to think a bit carefully on how you do that. And it's very, very difficult to formulate a multi-scale that captures the noise exactly. So almost always, there's a few examples I know of, but very few, where you can actually, there are special problems where you can actually make sure you capture the noise exactly. But almost always you don't. So, and so you can overestimate, possibly in some cases underestimate, but usually greatly overestimate the stochasticity of the system, which means that you may go into particular, you know, local steady states or local equilibrium, you may not normally even achieve. So this will mess up like nucleation phenomena, orders of magnitude. So things in nucleation are statistics of small events when something happens. So you can mess that up massively when you put things together. So the question is, how do you deal with that? Well, one thing we know is we know that the stochasticity in this is much bigger than the real stochasticity. So it's sort of an artifact of the length scales that we can do in our simulation. So what did we do? Well, we put in a filter. So this is just a low-pass filter. So 1 over tau s plus 1 is weak pulse transforms. And it's a standard trick you use in control. You just put a filter on a signal to make the noise less. But in this case, we know the stimulation noise is bigger than the real noise anyway in the real system. And so the thing is that this is an artifact because of the amount of KMCs that we can patch on the surface. In this case, represented 3D. And it ends up being a stochasticity that isn't really represented in an appropriate way. So what you do is you put in the filter. The other thing about filters is that if a system is barely unstable, a filter can stabilize it. So something you learn in feedback control. You use low-pass filter, you can stabilize the system. Now, if you do that in this case, all you do is you just filter this noisy signal coming in from the KMC. And this is what happens, which is exactly what the answer should have been. So there's this particular situation where nothing should have been happening. And we can see now nothing is happening. So the noise has been vastly reduced, okay? And it's clearly stable. Now the question is did we change the dynamics? Yes, we did. We inserted a filter. But you don't care about whether you change the dynamics of the simulation. Did you make the dynamics closer to the real dynamics? That's what you care about. And so you may need to introduce some dynamics that may be useful to introduce dynamics into a simulation or model so that its overall multi-scale simulation is much closer to the real system. Now we have a paper that was published in 2005 where we theoretically went through all the theory. So we wrote all these as formal operators, including noise terms. We did a whole bunch of operator mathematics to justify and explain why this theoretically is correct for this class of problems. So the way we did it is we represented another operator for the real system. Then we wrote out the equations for another operator for the model. We modeled each of those and then put it together. And because we had models for operators for the real system, we could try to choose this out so that we could get the dynamic close to the real system. So basically we created copies of both these operators and noise terms and we went through a bunch of mathematics and showed that putting in the filter actually helps. Now I'm going to tell you I talked about systematic design procedure. I'm going to tell you what the answer is here. So you don't even have to look at the paper. You don't want to learn a bunch of math. The filter needs to be low pass. Kind of makes sense. You basically want all the dynamics of the system that you care about needs to pass perfectly. Needs to be gain 1. So you basically just have a low pass filter. We want to choose the frequency, the cutoff frequency, such that it's the frequency that cuts off the noise that's not aphysical. It's aphysical, it's not physical noise, so it's not correct noise. So you cut that off, but you keep all the dynamics of the system. And so that's a standard thing we do for filter design anyway. So you go through all the mathematics to get the answer you expect. So basically what you want to do is you want to have the filter be fast enough to capture all the dynamics in the system. So fast enough time constant to capture all the dynamics of the system, but slow enough that you filter all the aphysical noise. Which is what you would expect, and that's what the mathematics does. So. Are there questions about that? Or? Okay, so now I'm going to talk about the last one. Now I'm not going to spend as much time about this last one because it's pretty advanced. So I'm just going to talk about it just because if you ever need something that's advanced, then you'll know where to go to learn about it. Or you should know about the method. Actually, if you're advanced enough to implement this method, you're probably advanced enough to figure out how to implement this filter. Okay, so, so I'm going to explain really the principles. Probably with the principles you'll be able to figure it out. If you have the skills to be able to do this, you have the skills to be able to derive it. And I'll describe exactly how it works, okay? So that way you know exactly how it works. So the thing about that other filter, the low-pass filter that we did, is that the low-pass filter did not have explicitly the dynamics of the two individual codes. So it's just a low-pass filter. And so you can actually do better in your filter design if you give it information about the dynamics of the two codes. And it sort of makes sense. More information, you can do a better job. And so that's what this filter does. So what it does is it builds what's known as an estimator. And this comes out in it's very heavily used in the systems and control field. Where what you do is problems where you can't measure the state directly, but you have measurements of other things. And then you use your model to estimate the states. So you might, for example, concentration is hard to measure typically, often, quickly. So you might measure temperatures related to concentration and a few other things, and then use like material balances to figure out the concentration entity corresponding to the temperature. And you do that because you know the reaction rate is X with that rate of heat to that reaction. So this is a technique that's reasonably standard. You often hear terms like Kalman filtering or Kalman estimation or particle filter. You hear these kind of terms. And so basically the idea here is to design one of those. So this is a case in which we have a code here, which I think, I can't remember whether that was 2 plus 1D. It was probably 2 plus, well, it must have been 2 plus 1D. But, and then what I'm showing you here is some points that were used in a continuum code. So there's a simulation grid that's been done, but it's been done very sparse. So instead of, when you're doing the simulation, this is all electrolyte, you would normally have like at least 10 points across the ball. Going up here, probably at least 30 points going up here. So the continuum code fills out this, it has a whole bunch of points. But what I do is I don't want to build my estimator based on that code because that would be very expensive and it would be a very big estimate. So what you do is you say, okay, I may have this result really finely by my continuum code I'm going to simulate. For my estimator, what I'm going to do is I'm just going to make a much, much coarser grid. And I'll write down the diffusion, convection, migration grid. So whatever the equation is for the system, I'll write down that PDE for this, but I just have a much, much, much coarser grid. Then I write down the differential equations for that. And what's nice about that is that the cost of that simulation will be very, very low relative to the continuum. It will become negligible. Because, as you know, as you increase grid size, it's a polynomial function to figure out what the computational cost is, and it's always very linear. So you can end up dropping this grid size down by order of magnitude or so. And then the computational cost of doing this simulation will be negligible compared to the cost of solving the entire finite difference code at high spatial resolution. And actually, in this case, I think the full one was something like 10 across. So the cost of this was like 0.001% of the cost of all that. So very, very, very cheap. So we basically created another model, but we just did it very, very coarse. Now, so it's very cheap, so that's advantage one. Advantage two is that it still has the basic physics in the sense that it won't get the resolution really good, but it will get like the migration, the amount of migration, the amount of diffusion, all that sort of main flow will be captured. All the main physics will be captured. You just won't have the very fine resolution. So then what you do is you design a filter. So if you remember what the issue is that the KMC code is creating a lot of stochasticity. And in many cases, because of coarse graining or other problems, lack of enough sites, that noise is much bigger than the noise in the real system. So you want to have some way of translating that noisy signal down to a much more realistic signal to be sent to the continuum code. You're basically making the boundary conditions much closer to the true boundary conditions for the system. And so in this particular case, it was passing, I think this was in Pohl's code. And so, let me think a little bit more. I remember now. Back up a bit. This actually was a 3D KMC code. So actually, the 3D KMC code goes all the way up to here, and the finite difference code is up here. Yeah, he could. I should have this in this one too. Okay, take that back. So this actually was a KMC code. So what he's done though is he has implemented continuum code in here. Okay. So you have a continuum code here, but it's discretized coarsely. And then he's got another continuum code up here. And then here he has a 3D KMC code. But what he's done is he hasn't shown all of the ion points. He's only showed just the points that are on the surface. Okay, so then what does he feed this filter? So the idea of the filter is he wants to figure out what the concentration profile is here, because he wants to feed that into the other code. Why? Well, it turns out this was before we learned the lesson that you need to have the flux and concentration in the order that it should be. So in this particular version, he's trying to pass the concentration up, and he should try to pass the flux up. But again, this was done about 10 years ago. So the question is how do you do this? So if I want to come up with a concentration profile here, the problem is that this 3D KMC code, which is coarse grained, gives you a very noisy concentration profile here. And it's not realistic, because all of that noise that's being here is being propagated up here. And in reality, when you look at the various length scales, this length scale is large enough and it's filtered enough, it should be a smooth curve. But unfortunately, 3D KMC code is treating stochastic all the way through this fluid region, so there's no damping. So what did he do? The way he did it was, he said, okay, what I'll do is I'll feed the species flux at the surface, which he knows. He could do that from the 3D KMC code. He then fed in surface morphology as additional information that might have some influence. Turned out the effect was small. And then he fed in the points that he got from the KMC code in terms of the concentrations in the upper region, so these upper points. And the idea is that what he can do is he's feeding information from the KMC code, but in this filter he puts in the continuum equation, of course, for this region. And the thing is, the continuum equation doesn't have any of that aphysical noise in it. So then what he does, he designs what's known as a common filter to figure out what is the best estimate for these particular states on the surface, given these amount of information, and the model which connects this concentration profile to all the concentrations at the upper interface, the species flux at the interface, and the surface morphology. Do you understand all of that or not? It's pretty advanced, but so for a control engineer, you would understand it pretty easily because it's a control concept. But the idea is you're basically defining an overlap region. So this kind of approach has been applied a lot. It's been applied including by a lot of people in Illinois. Where what they do is they'll have a continuum code and a stochastic code in the same region. And then what they'll do is that transition allows them to sort of isolate sort of a bunch of noise which may not be quite correct from influencing the other code, as well as improving the numerical stability, the numerical reliability of the deterministic code, because you're not feeding in a bunch of extra noise. The thing about the literature, though, is in the literature, these overlap codes are sort of, they propose them and they apply them and they see if they work. The thing about doing it this way is you actually have a mathematical framework for deriving them. Okay, so that's the advantage of this. The disadvantage is that you have to learn about state estimation. Okay, so that's the disadvantage. So it's a pretty advanced method, but it is a method that there is a systematic way to step-by-step derive ways of having smart overlap filters that manage the information between codes. I think if you want to do it, you probably want to go find your code control engineer. That's what I would say, though, because you have to learn about estimation theory, so it's better to have him do this, or him or her do it. So the final conclusion is that a time-varying filter equation was obtained by application of the finite volume method in here to solve the continuum differential equation, even though it's in the permanent angle. So then that provides the filter. And it says it's related to the multiscale overlap. So there's large literature on that, but not really systematic or general types of approaches. So now I'm finished with the guides for implementation. So what I started with is I tried to keep things at a relatively simple level and only do the very advanced stuff at the very end, and then have the stuff that is stuff that you are fairly easy to implement early and stuff that's very hard to implement at the end. So the first was having to deal with conservative methods. So the amount of effort to implement a finite volume code is no more than a finite difference code. So that's the case. It really doesn't cost you anything more, and you get this huge advantage that I showed in the example in terms of using conservative code. So you'll be much more numerically stable for the multiscale code. And it's kind of good to conserve mass moles in charge anyway. So it's kind of good to conserve properties, not be leaking material somewhere into limbo. Then we have the select order of passing boundary conditions. So I gave an example that was really simple, and you say, well, it shouldn't matter, but unless you iterated to convergence of boundary conditions, you ended up getting numerical instability that's quite severe in a short time. We also talked about how you can use a lot of the insights that are already available, a lot of the tools from
implicit solution of differential equations, differential algebraic equations, as well as numerical analysis of differential algebraic equations, to select the trade-off between numerical accuracy and computational expense. And basically, methods that pass information sort of like an Euler method have accuracy like an Euler method. And methods that converge, that act and operate like a predictive corrective method have accuracy like a predictive corrective method. So the number of iterates required to converge an implicit solver when you're doing multi-scale code, you know, it's more or less, at least for deterministic multi-scale codes, is more or less like any sort of implicit solver. So if you're iterating to convergence. And so you have some trade-offs, and you have the plot that I gave you that shows you clearly how the accuracy is weighted to the computational expense. Then we talked about this idea of filtering, which is still very, very easy to implement. So you basically insert the low-pass filters. I gave some references that shows where you can look to see the theoretical support. But even without the theoretical support, if you just use your intuition, the answers you get from theory tells you what you would expect. So you basically want to use a low-pass filter that captures, that's fast enough it captures all the dynamics of the system. Typically, it's all the dynamics, maybe an order of magnitude faster than that, to make sure you've really captured everything. So choose your cutoff time, or your time in your filter time constant to be about 10 times faster than the dynamics you care about, but still it's slower than all the noise that's any physical in your system. And at the last bit, I just had a very brief glimpse at the much, much more advanced method. So how would you systematically design an overlap algorithm to manage the information transfer between a stochastic code and a deterministic code? What I have here is really just a simple copper or electric deposition. This is just a picture of the stuff that motivated a lot of our systems. And this just shows some of the super filling. These are just filling of trenches for the copper. And this just happens to be the most complicated multi-scale system we looked at. So what I'll do is, I'm just going to go through this one slide to show you, how advanced some of these can be. So what I'm showing you here is a case in which this is one of our later simulation codes where we have coupled 3 different codes. So we have a finite volume method. Well, remember, one of our guidelines was to use a finite volume method instead of finite differences. We explain why. So this time we knew that. We did the boundary condition passing in the right way, so that was guideline 2. So the concentration potentials were passing from here to the KMC code, and fluxes were passing back. And I talked about the importance of choosing the order of the boundaries based on the physical insight, based on the physics of the system. So we followed that rule. We couldn't do a KMC simulation along this entire solid liquid interface. So all of these green refer to different patches that were used. Keverkes calls this the gap tooth method, but these kind of notions have been around for a long time, even if you do like contour plots, where you'll sort of do an interpolation between points. So in this case, we're calculating properties of each of the KMC, and then doing a spline-like fit along to figure out what it's going to be along the entire interface, so that we can fill in the missing information before we find all of the code. And so this just shows, those are actually real KMC results I'm showing you here. And this just happened to be flat, just to see what the, not doing KMC be next to the KMC. And then the total experimental time you're simulating is 300 seconds. That's how long it fills up one of these trenches of copper. You can see the information is being passed there. What I haven't talked about that's important, you pass fluxes, but this copper is actually moving because you're depositing copper. So you also have another code, which is a level set method code, and that's simulating the interface motion. And that's a very robust, very, very nice, simple implement method for moving parameters. And there's a huge literature on this, and this just happens to be some of the big papers. You can pretty much implement this up in that, read a paper, implement that. It's pretty easy method. That's why they become very popular. So we have to feed the fluxes to that because the fluxes of copper is what's deciding how fast the copper interface is moving. And so then you feed that information to a moving boundary code. And then you have, and then you pass the interface position back into the finite volume code. But you also have the fluxes. The fluxes also pass the finite volume code. So you pass both the interface and the fluxes to the finite volume code. And then that's the iteration. And then you have time scales from nanoseconds to milliseconds to 300 seconds. And like before, this was iterated lots and lots of times.
So you iterate this up to the time scale that was important here, and then you do averaging, and then pass the information to the receiver.
So it follows all the guidelines and all the rules. So again, these were the guidelines. So prefer conservative methods over non-conservative methods for implementation of continuum pilots. That particular choice, use finite volumes, conservative, KMC, which is conservative, and mass boundary conditions exactly. So we consider charges, moles, and mass for each of the subunit as well as for the overall system. Selected the order of passing of boundary conditions between codes based on physical insights. So we had an example earlier where I showed you the danger of not doing this. And so even when it seems like it worked. And so this is the very prototypical example. So potential and surface concentrations need to be fed to the KMC code. That's what makes sense to the physical chemistry of the system. Fluxes are then passed over to the finite volume code. Utilize accuracy estimates from numerical analysis, select trade-offs between numerical accuracy and computational expense. Many iterations per linking time interval for this problem is just too expensive. So we knew we were going to be limited to first order in time. So based on the plot that I showed earlier. If needed, incorporate a filter to outputs of stochastic simulation codes to improve numerical accuracy and stability. Of course, especially if that's aphysical noise. It's noise because of the limitation of your computations as opposed to the physics of the system. In this particular case, we needed to filter for the species with very low fluxes. Okay, for that particular one. Because at very low fluxes, what was happening is you get zeros, non-zero, zeros, non-zero. So that was causing. And it was not physical, it was aphysical because of the limitations of our resolution. And so then we used the filter for just those species. We actually didn't filter the other species, we didn't need it. So we only filtered the boundary conditions that were being passed and needed. And again, we made sure it was fast enough to capture, that we weren't filtering out dynamics of the real physics that comes through the system. For acknowledgements, Professor Alkire and I would like to acknowledge Tim Drews, who did a large portion of the work, Juan He, who helped me, and Mo, which helped me with the guidelines and the simple examples that was shown during the presentation. David Ma, who's the guy who implemented the filter approach, and Lily Delagiani at IBM, who was our contact at IBM to help us work on a lot of the examples, as well as providing chemistry and stuff for the problem. And then the funding agencies for the stuff that was presented to, which was IBM and the SRC Corporation. And I'm now ready for any more questions and discussion. So, go ahead.
In the first two methods, you had only a single battery. In the first method, you had an overlap where you did both methods and then you compared it through the filter.
Say it again, go ahead.
In the first four cases that you showed, you had only one single boundary when you passed the conditions. In the first method, you had overlap. So there was a small region where both codes worked together. You found results and then you sent it to a filter, and that would basically.
Yeah, that's right. So what we did is that the continuum code for the overlap method was the concentration profile at the top of the overlap region. And then the overlap region was all actually inside the KMC domain, right? But what we're doing is we're solving a continuum inside of the KMC domain. But we don't have to resolve it to high spatial resolution because we just need to have enough of a model that we can filter out all the aphysical noise and still capture, that there's migration and diffusion. It still has the physics, in the system, and that's smarter filtering just putting low-pass filter. And now we actually have the physics of the continuum phase. So we're basically inserting like the continuum phase right into part of the games, the Monte Carlo domain. You follow?
The fourth method was removing the aphysical noise. The first method was the estimator for parameters that you're using. The first method is like an estimator for, say, concentration by using temperature.
Well, the last method that I had there was 5. That's where we're using, you can feed any kind of information. Any kind of information that's related to your boundary condition you'd like to transfer, set. So it's easier for us to do it. So in this particular case, the thing about this is that, so the earlier method was this low-pass filter approach. Okay, so that's easy. But see, that low-pass filter approach, I could have used it here. So we did have a KMC code. We could have just used low-pass filter, whatever this concentration was. So you could have done that. But the problem with that is that it hasn't exploited the fact that this is really, this whole domain, this continuum domain, is really coupled by material balance and diffusion and migration, right? So there's a whole bunch of there's a variation in potential as well as concentration filter. So all of that smoothness isn't in the low-pass filter. The low-pass is just a spot filter in time, not in space. Okay. And so this particular case here, if we take a concentration profile, I would like to get the time and the space resolved well. So for example, I don't want to have a lower and higher point wiggles here because of stochastic of the KMC. It's not physical. Okay. So that meant that the low-pass filter approach, which is easy to implement, very nice in that regard, doesn't really work very well in this case. I could filter out time stuff, but it will ignore the information in space. So by using a state estimator, what that is, I can capture that information in space. Right? It's a lot harder to design. I mean, you have to have more sophistication. If you're sophisticated, you know how to design states, which is not hard. Okay? But it requires a lot more sophistication in background design than a state estimator. But a state estimator can capture it because instead of just being low-pass filter, you're feeding it all of these behavior of diffusion and convection and zero bound fixed law, all that's embedded in that model that you're using. So it has all that information in the filter. And then as choosing the inputs, I want to choose the inputs anything that I think will help my concentration profile. So what we did is we chose the species count, which is basically the concentrations according to KMC all at the top. Well, that's clearly going to be useful. It's noisy, but it's useful. It's going to be very useful for estimating concentration profile. The species flux at the surface, that's also useful. That's basically defining the boundary condition that I'm going to use in my continuum code there, right? So that's really useful. So now I have a boundary condition here, and I have basically boundary-like information here. Now I have boundary. This was a periodic boundary condition on the side, so I don't need any other boundary conditions there. So now I've defined all the boundary conditions, and I have the dynamics. I know what the diffusion coefficient is. I have an expression for the migration coefficients. You see what I mean? I got a potential. So with all of that modeling information, the two boundaries, and knowing what was the concentration profile in the previous time, I can do a much better job at predicting what the next concentration profile is. You see what I mean? I'm glad you asked that question, because my last question was a lot better than my earlier one. So, thanks. But yeah, you have to know how to do state estimation. So it's not hard, it's just more, if you're good at math, it's not hard. But, there's tricks in that too, in terms of, you can try to do the simple approach and be as good as better approach. There's tricks in any field, right? So the purpose of this is just to give you tricks for this field. Or pitfalls as well, and guidelines. Other questions? Or?
So if you really want to do the copy you may have in the beginning of this distribution, like you want to, let's say, from different level of the distribution, this is in parallel with matching this still kind of, do you still worry about this?
Yeah, well, definitely. So, I mean, if you can solve the original problem without decoupling things, do so, right? So, but for these very complicated systems, you can't. So that's sort of the difficulty. So if you take this particular example here, the thing is there is no way to tackle this problem correctly. So the length scales that we're talking about here, these were I guess 100 nanometers or so. But if you look at the current trenches, they're much smaller than this. But there's no way you can solve, for example, KMC code for this entire domain. It's just not possible, right? So there's also not possible to even solve KMC even on the interface. It's not possible. So that's why what we did is each of these KMC codes that are written, we're just doing spot checks, and they're being chosen so that the concentration and potential here isn't so different from here. Now, I just showed 10, but the top one's at 30. So you need to have enough points here to sort of resolve the concentration potential variation along this interface. All of those KMC runs were completely in different processors. So each of the KMC run went to a different processor. And then we had the finite volume went to another processor. I don't remember if we parallelized that to multiple processors or not. But when we ran this in parallel with all these KMC codes, the rules we followed about the boundary conditions here was exactly the rules from the one edicts. So in this case, flux length of finite volume and concentration potential. Yeah. So those rules have to follow in every place where we have a boundary condition between two codes. You have to follow that guideline line. The finite volume use the conservative methods, use methods that conserve properties like mass moles. and charge, those have to be satisfied. Those were satisfied here and for each of these KMCs. Right? So they satisfied that other guideline. And then the filter trick was yet that other guideline. And so those kind of tricks, we could have done 100 of these in parallel, right? So, and so those tricks, even though my simple example was just 2 codes, when we actually implemented, this is the actual problem motivated everything. It actually was implemented as lots of codes. There's a lot of codes in parallel, so multiple KMC codes and continuing code. So, you see what I mean? So the same guidelines work. You just apply them at the interfaces between each of the codes. So the conservative methods, that applies to each block. So you take every code, make sure it's conservative. Does it exactly conserve mass, moles, charge? And its energy, momentum. So anything is conserved properly, make sure it's exactly conserved. So the easy way to do that is to find volume and go conserve that. If it's KMC, you get automatic, right? So you look at the method, make sure each piece is conservative. So that's kind of like volume. Then when you put them together, then you say, what is the physical chemistry of the interface that will govern the information passing? It should govern the information passing. So you want to pass information between boundaries so it's consistent with the physics of the system. Okay. And I showed an example where if you don't do that, it can be like disaster, even though it shouldn't. You wouldn't think it would be mathematically. When you actually look at the results, it is a disaster. So you really want to, or you have to use like really tiny delta t's, or you might be forced to a full iteration. You might be able to do, super high concurrent and not very good results. So it's much better to use your physics, but then you do that on each interface. So let's say I had 3 codes that were like 4 codes that were like in a box. So each of the interfaces between those codes, you want to look at the physics and chemistry of the system and argue, what is the information passing to be self-consistent? Now I mentioned earlier, if you iterate to convergence, it doesn't matter. If you converge all the way so that the errors go away, it doesn't matter. Okay? But if you link them with something like KMC, you can't do that. Or it's very, very hard to do that. Right? Because if you link to KMC, when you run the KMC code the next time, that you get the stochasticity, so you'll never get a convergence. And there's a trick you can do where you can fix the random seed, so that you basically give you a fixed random seed. But the problem then is KMC has varying time. And your time will mismatch, you still have noise. So then you got to try, and then you got to try other tricks. So it ends up becoming very messy if you're lumping something like a stochastic code to, coupling dynamically, stochastic code, deterministic code. There are tricks, but they're not easy to implement. They're a bit of a headache. They're not very satisfying. You know what I mean? It's very hard. So that's why you end up doing tricks like this, where you're basically you're not iterating convergence. So you get higher speed, you get lower accuracy in time. Okay, you get higher speed, and then you try to make sure that I focus really on the first example is focused on that, but you get higher time, faster speed, lower accuracy, but an algorithm clearly can work forward. And then I talked about these other tricks about filters and estimators to try to get rid of any physical noise that may be introduced. And then this example, you also need to think about spatial accuracy. So what is your spatial resolution? So in this case, you want to make sure that these points are close enough that you capture the spatial resolution of the interface properly. So that's even another issue, which I talked about here at the end. And so you basically need to sort of systematically look at all the interfaces between codes, spatially and temporally, so versus time and space, and make sure is the information time passed appropriately, and then is the spatial resolution sufficiently high for what you're trying to simulate. And then you need to ask that question in between the interfaces of every code that's in your overall simulation.
So we try to decide the best, let's say, how many this space resolution is. You have to do it many times to do oscillations to get an idea of
that's one approach. You can get a rough estimate by scaling analysis. So for example, if I have transport along the width, we do this a lot. So we're doing transport along the interface. Then what you can do is, if your transport's through the bulk phase, you have diffusivity, or if you're doing surface diffusion, you have diffusivity. So either way, you know what your diffusivity is in the system, at least what you're simulating. The real system may know what it is, but you know what your simulation constant is. So as soon as you know diffusivity, you can calculate a time scale or how much distance you can move in a time scale. And that's because by scaling analysis, you know the diffusion coefficient has to go as L squared over tau, where L squared is the distance in which we move. We could call it R squared over tau. You follow? And so by that scaling analysis, what you can do is you can say, okay, within this particular delta t time, because you know what the delta t update is, you can specify that in the code, how much will a molecule move sideways along the interface? Okay. So you say, okay, d is equal to L squared over time. So I'm going to put time on the other side. Time is now delta t. So So I have d times delta t equals L squared. So you take the square root. So you get the square root of d delta t will tell you the distance in which molecules can move inside by maybe 60% of molecules might move. But if you take 3 times that, almost very few molecules will move farther than 3 times that at the time scale. See what I mean? So you do 3 times square root of d delta t, and that'll tell you roughly how much you can move sideways. So if you really want to be careful, you want it that close. Okay. Computationally, usually for something like that, you can't do that. You don't have the computational space. So then what do? You say, okay, well, it gives me a bound, but I can't use that bound. Okay, I got to make them farther apart. So then what do? The way you do is you do this with 10, and then you report those concentrations. You just plot it as a profile. Concentration as a function of space, and then over time is the 3 plot. And then you say, is there stochastic fluctuation this way? And then, how much variation? So what's the delta C between here and here? And I've got the rate expression, so I can see what the variation in rate would be. You see what I mean? But then you could also argue it depends on what you're trying to simulate too. What you really care about is just, let's say, the distance it's moved. You may have some of those not resolved quite so well, but if it has a weak influence on the distance moved, then you may actually use a partial resolution. So it also depends what you're trying to simulate. This is actually sort of a theme that's also related to what Maud was saying in Tuesday and Wednesday. So when you're dealing with these very complicated systems, you're not going to be able to simulate everything. So you have to think very carefully about, what parts of the model have to be really simulated, okay? And then what resolution do you need in different pieces? The harder the system is, the more you have to do this. Simple system, you're only doing this. It's coded up, it's done, okay? But the more it gets multi-scale, the more likelihood you're going to have to think more carefully about exactly how this information is passed, exactly what's the resolution, exactly what do I care about. So, you see what I mean? And typically when you solve any code, this is true in general, but it's probably more true in multi-scale. You always have sort of the key pathways, and those key pathways dominate. And then you have a bunch of other pathways that may be important, but their rates aren't really influencing things too much. Maybe, for example, chemical pathways, there might be a lot of fast things, and they might have some slow thing that's a bottleneck. And so the actual bottleneck is a bottleneck of all of the chemistry that actually gets you to your product. In that case, you don't need to have fine resolution for all this other stuff, because it's all going to get to the bottleneck anyway. If it gets a little bit slower, a little bit faster, but it resolve this very much. You see what I mean? So some of that you can do by scaling analysis. So I give you the example of lane, but you can also do time scale analysis, very similar. Get a sense. And then as I mentioned parameter sensitivity analysis. That's why we were doing that in that corrosion example. So by doing parameter sensitivity analysis, we do the sensitivity with respect to every parameter. And then if I see a chemical pathway in which all the sensitivities are low, then I know that none of those parameters influence the variables I care about. You see what I mean? Now you have to be careful because you don't want to throw the baby out with the bathwater. So let me give you an example of what a mistake would be. A mistake would be is you see a chemical reaction in which you have low sensitivity and you delete the chemical reaction. Very, very dangerous. Okay? Because you may have deleted the only pathway from the reactants to the products. You see what I mean? So you have to be very careful about deleting chemistry and physics from the problem. But for most of the parameters, the final results won't be sensitive. If you have like 50 to 100 parameters, at least usually half of those won't be very sensitive to those things too much. Many of the chemical reactions, you won't be that sensitive. So they'll be much less sensitive to sort of what's exactly happening in the interface, for example. So it's good, so whenever you do a code, you need to also think, when I write a code, I think about what am I trying to do, right? Before you write, any code or anything, right? Just, what am I trying to do? What am I trying to simulate? What should be important? And then I'll put everything in that I can, all the physics I can. If I can simulate all of them, I'm happy. Okay, I don't have to waste any time. But if it ends up, I have to start thinking shortcuts about how many points along the interface and stuff, and I have to think a lot more carefully. You follow? Okay.